So, good afternoon, everybody. And I'm happy to host for the keynote Fred Van Eeuwijk from the Wageningen University, which will present his work on statistics for phenotyping. So thanks, Fred, for being here, and I think you can start.
Okay, thanks. Everyone hears me? Yeah? You also see my screen or not? Because I don't hear anything at the moment.
Yes, we can see you.
Okay,
and
okay.
We can hear you.
Yeah, thanks for inviting me and also saving me from a day on strategy and management. I mean, once a year we are obliged to attend such a day, but of course I had a very good excuse for having to present in this conference. Okay, this is work with a lot of people, and I've taken two examples of kind of work we're doing, let's say, in relation to how to use statistics for analyzing phenomics data. You can see on the one hand, I'm talking about outlier detection. On the other hand, I'm going to talk about the prediction of plot and trial quality using information from phenotyping devices and platforms. So, well, to sketch a situation that all of you know rather well, I mean, nowadays, with all these new devices, sensors, proximate and ultimate, we have a lot of extra information that, wait, I will put my laser pointer on top so you can see what I'm talking about. I mean, the data that we generate on the one hand, initially are high dimensional. We get images, we get spectra, etc. Typically, something needs to be done with these images and spectra, so kind of features are extracted. And well, this can be done by deep learning and all kinds of machine learning techniques. And then we end up in a situation that we have some kind of trait that can be interpreted in a biological way, and it can be followed over time. And actually, I think the situation I'm going to look at is that we have multiple of these plant trajectories over time as generated by the platform. And one of the questions that arose in a collaboration with Scott Chapman, and I will say more about the project later on, is it possible early on in the growing season to predict the quality of plots and trials for yield later on in the season? And the idea behind this is that, well, if early on in the growing season you can see that the trial is going nowhere or that certain plots are going nowhere, you don't need to keep on observing those plots or fields. So, well, that's an interesting question, and in principle, it looks like one that we should be able to solve. So I will show you some results of where we are at the moment in a minute. Now, when I started to think about what to do with respect to this question, it came to my, you can see my screen. It came to my mind that actually, if we want to know whether a particular plot or trial later on in the growing season is going to be deviant, that's a little bit like predicting an outlier, predicting an outlying plot, predicting an outlying field. And so I also remember that we have done a lot of work over the last years within the context of the EPPN 2020 project on the identification of outliers. And well, I think all of you know that when you do a classical statistical analysis, you can check on some of the assumptions, but you can also look at, well, for outliers, and we have typical diagnostic plots for that. We look at the residuals versus the fitted values. We look at the residuals versus certain factor levels, covariates. We make these QQ plots to check for normalities, etc. If you have done some G by E analysis, you can look at AMI biplots to figure out whether certain genotypes or environments are deviating from the rest. Now, of course, this we typically did in the past for experimental fields on which we observed yield or other traits when the experiment was done already, but now we're in a situation that we hope that we can extract this kind of information early on. So the projects that I will refer to are, let's say, three of them are on this slide. Probably Scott has talked already about the Invita project in Australia, in which we are involved from Wageningen. And the idea here is that we're looking at the efficiency of the variety trial network for wheat in Australia. And very importantly, we're trying to investigate what the addition of especially phenomics information would add to the quality assessment for the varieties, and also estimating the difference between the varieties in those networks. And so can anything be gained by using phenomic information? Well, more or less the same objective is defined within the European INVITE project. You see the abbreviation there. I think many of you that are there in the audience actually are involved in this project. And also there we analyze networks of trial data for a number of crops, not only wheat, also maize, sunflower, perennial ryegrass, etc. And also there is the question, is there anything gained by including phenomics information on our classical VCU information? A project that has just finished, and that was led by François Cadieux, was of course the European Plant Phenotyping Network 2020. Well, I think also I saw in the list of participants that many people know about this project. I will start off with saying a little bit more about the EPPN 2020 project. I was the leader of the joint research action number 2 in that project, and well, there were 3 main tasks, and let's say for this talk, especially the first task on data quality is of importance, and let's say the people that did a lot of work there are Emilie Millet, Nadine Hilger, and Isabel Sanchez. And I will show, let's say, what was developed, especially by them, on outlier detection. And well, this outlier detection then served, let's say, to annotate the quality of the phenomics data as part of a quality pipeline. So, well, I think before you start to do this, you need to do a little bit of thinking, also conceptually, and actually, what is an outlier? This sounds a bit trivial, but I think a definition that will help us on our way is that an outlier is actually anything that deviates from the general pattern that we expect. And of course, well, what kind of patterns do we expect in our data? Well, I mean, we can know our system biologically so well that we can already a priori define what the dominant pattern should be, and so we should be able to flag potential outliers. But of course, more usually, we have to fit a model to the data statistically, a kind of heuristic descriptive model, and based on what the majority of the observations do, we can identify certain observations that look a bit curious in the light of what the majority is doing. And well, in the best situation, we try to use our biological insights to direct a little bit the fitting of the statistical models, because when the statistical model is more elaborate, it will follow the data more closely. But to follow the data more closely, in principle, you should not use too many extra parameters. It's fine when you can do that based on biological prior knowledge, so then you can force the model to stay close to the data, well, based on something that is outside the data itself. I mentioned already, I mean, how do you decide when a model is correct? Well, we have goodness of fitness measures, we have information criteria, we have cross-validation, etc. There are many ways to do that. And as I mentioned, I mean, when is a model good? Well, actually, when it's predictive for the majority of the data points. And in our case, what we're up to is, okay, am I able to predict from images, drone images, spectra obtained by cameras on my drone or from satellites? Can I predict whether a plot later on in the growing season is going to be deviant? That is the question. Now, to refresh your ideas a little bit about outlier detection, on the left, we have, well, classical ways of identifying outliers in univariate data for single traits. And well, I think this is a nice example. Here you have a histogram. Majority of the observations are more or less belonging to this almost normal distribution. But you see there are a few to the right, and here's a clear gap. And that makes us think that especially this observation here at the right is suspect. Well, these other ways are also, these are similar examples of when you observe a gap with respect to the majority of the data, that probably this might be an outlier. And when you want to make an assumption on the distribution that is valid for the data, well, for example, a normal distribution, well, then you know that anything that is beyond 2.5 sigma from the center might be suspect. If you arrange that, let's say, for 2 traits simultaneously, well, you get in all these functional relationships, and the idea is not very different. If you're able to come up with a functional relationship between the 2 traits, then any observation deviating from the functional relationship for the majority of the observation will be suspect. And this is an easy one. Here you have a function in which the red ones clearly are outside the rest of observations that are mainly blue. So the blue ones are in the model and the red ones are suspect. Well, in a sense, here we fit a bivariate distribution, and anything that is far from the bivariate distribution is suspect, not very different from what we see on the left. If we go to higher dimensions, well, actually, the funny story is that rather quickly we run out of extra instruments for higher dimensional data. Yeah, we can plot them in scatter plot matrices, but we can do that well for up to about 10 trays, because otherwise we cannot inspect these things anymore. We can look at heat plots matrices for the correlations. Of course, the biplots based on PCA analysis are quite popular, but once again, if you have more than 20, 30 traits, and this is also difficult, well, you can cluster, etc. But the story every time again is, I need to define a model, and everything deviating from the model might be an outlier. Now, more relevant even to us is what we're doing in terms of time trends, because I think a differentiating feature of the phenomics data nowadays is they are longitudinal, and they are repeated observations on the same plants and plots. And well, here you have a few examples in how to figure out where the anomaly is. But if you look at this trend here to the right, which is not that uncommon for all kinds of phenotyping platforms, here this looks fine. But you need to superimpose a few cyclical trends on top of each other, and well, deviations from that might be suspect. Okay, this is to refresh your memory. Now I need to say a few words about the models that I want to apply before I can tell which observations are deviating. And here, there's a rather essential choice to be made, because if I know the biology really well, I can use a statistical model inspired by the biology. If I think that a logistic equation is valid, I can fit a logistic equation. I can check whether my observations deviate from the logistic functional relationship. If I don't have a clear a priori ID, and that's often the case, well, we use what we call splines. And splines is a very flexible regression tool, and it's not that complicated. I mean, here you have a situation in which we have an independent explanatory variable, and we want to figure out whether we can use that explanatory variable to describe functional relationship with a trait. But of course, this explanatory variable can also be time. So for you, we have something here that can be called time, and we want to model, let's say, a particular trait. And instead of using the initial time measurements or using the covariate measurements, we replace this single covariate by a number of so-called basis function. Here you see one example for such a basis function. Here you see a number. And what you see here at the right is in one dimension what we will do. And if we want to fit a relationship, we simply need to estimate coefficients with respect to each of those basis functions. And if you do that in 2 dimensions, it looks like these storage devices for X. Then once again, our task is to find the proportionality constant for each of those little mountains so that I'm able to fit a 2-dimensional surface as closely as possible to the data. What does it mean in terms of the design matrix? Well, for a covariate or time, you would have just one vector, one column in the design matrix. If I use those basis functions, actually, I define the values for those basis functions for each of the initial values on the time or covariate axis. Now, to make it a little bit more clear, here we show an example. The blue one is a simulated data set. The blue one is the relationship, the function relationship. We do some noise on top of it. These are the blue observations that you see around the blue curve. And here are our basis functions. And our task is to find the right multiplier for those basis functions so that the sum of them starts to approximate the blue curve. Well, here is a situation in which we're overdoing it. The rather wiggly red curve is the fitted curve, which is a little bit following too closely to the observations. Here we're underdoing it. We're just fitting a straight line, which clearly is not following the curvilinear blue real function. And here at the right, we're doing it correctly. We have found the proportionality constants that allow us to fit the blue curve as closely as possible. Well, how do we do that? Once again, there are all kinds of tricks, but it's still simple regression. And I think the additional thing that we need to do is we're fitting a lot of coefficients, because for each of these basis functions, we need to find a coefficient. Well, to do that, we need to make extra assumptions on the behavior of those coefficients. And either we make distributional assumptions in the Bayesian context, or we penalize the coefficients, for example, by requiring for the betas need to be similar for, let's say, close by basis functions. Quite a number of ways of doing it, not something that we need to worry about. Now, in the EPPN 2020 project, we have here an example in which we want to figure out whether a single observation in a time series describing a trait on a plant or plot is deviating or not. And the red line is, let's say, the fitted spline with respect to the black observations. So the observations were done and they look like black dots. We fit this red spline. We are able to put a green confidence region around it, confidence band, and any observation outside the confidence band for the spline, we might label as being suspicious. And here this is done for 2 different plants. Well, I think this is a very nice way of trying to identify outlying observations. And of course, it's up to the biologist, the geneticist, to figure out whether this outlier really also is biologically an outlier. But using a spline, we have a very flexible way of fitting a decent function, and we have some way of detecting the outliers. Here, we're making a little bit more complicated because it's not just a single observation in a time series, but we want to identify an outlying plant or an outlying time series. So here you see a number of plants, a red plant, a green plant, a blue plant, followed in time. Once again, we fit a spline over time. And if we want to identify whether the total of the curve or the total of the plant is deviating, well, we might simply look at the fitted values for the spline, and we might correlate the fitted values between the full set of plants. And let's say any deviating correlation will point to a plant that might be suspicious. And here at the bottom, we identify a plant with lower correlations with the other plants than is average for the other plants. So this might be a slightly suspect plant. Of course, with the naked eye, you can also immediately see that the one here, the blue one on the bottom, is a little bit suspect. You can also do principal component analysis on these fitted values. I mean, we'll give more or less the same results. Okay, so if your goal is even more ambitious and is not just a single time series for a single trait that you want to identify, but you want to identify an outlying plant on multiple time series, well, in a sense, you can follow the trick that I just showed. You fit a spline to each of the time series. You check on the fitted spline whether it deviates from the other fitted splines. And then the next thing is, for a particular trait, you label whether it's deviant or not for a plant. And you do this also for other traits. And well, if any plant has 2 or more deviant traits, sorry, if a plant has if any plant has 2 or more deviant traits, outlying time series with respect to the rest of the plants, you might say, well, something might be going on. And if you want to read more about it, I refer to this paper, I think, which is a nice paper to summarize what I've been telling you. I think I'm running out of time. Why is this? Okay. So there is software to do all of this, has been developed within the EPPN 2020 project. It's on R. I mean, here you see the reference. So, well, if I conclude, I've shown you different ways of identifying single outliers, time series, and let's say multiple time series. It may be good to say that before we fitted the longitudinal trends, we actually spatially corrected each time point for the whole of the platform. And then we, let's say, went on to take the cleaned data after spatial correction for this longitudinal analysis. Theoretically, it would be better to do both the spatial and temporal modeling simultaneously. We can do that, but it takes a lot more time. And actually, in practice, it doesn't pay off too well. Let's go to ground cover. This is for Invita in Australia. We have estimates from ground cover taken from photos, images taken by drones. And we want to know whether we can predict from these early estimates, the early assessments of ground cover, whether we can say something about yield later on in the season. And we verified at this moment, let's say the following steps. We could look at whether yield and ground cover correlate over time for particular fields. And we can also ask ourselves, can we predict yield as a function of ground cover? We can also look at the heritability for yield and see whether the heritabilities for yields across a number of trials follow the heritability for ground cover at any of the time points or integrated. And another thing that we might be interested in is, are there environmental conditions that allow us to predict how the correlation between yield and ground cover will develop? And at the bottom, you see all the people that have been involved in this work. So before we go, let's say, to have a look at the correlations between yield and ground cover, I want to emphasize, just like I did already before, that in any analysis of phenomic data, typically we have to clean the data for all kinds of spatial trends. Now we developed a special on spline-based, well, a spline-based method to do this cleaning. And actually what we do is we have the response, we fit a two-dimensional surface. The deviations from the surface have a genetic component and an independent error component. The surface, well, the surface you see on the left is built up from a few components. These components, well, actually are variance parameters, contain variance parameters that we estimate by mixed models, but that's not so important. I think what you can see here at the bottom is actually the basic idea. The raw data are decomposed in a spatial trend, the blobs, the genetic effects, and a residual. Well, this blob is typically we take the blob and the residual again together if we're going to do a multi-trait mixed modeling later on and remove this spatial trend because this complicates our life a lot in all kinds of genetic analyses. If we do this over time, you see at each time point you fit this spatial model, and we can also make these spatial adjustments that are close in time, that they become more alike when they are further apart in time. Two examples. This is a wheat trial. Well, you can easily see what the surface looks like. These were the raw data. We played around with higher resolution information. Here at the right, you see that we use higher resolution information coming from the drones and satellites, no, especially from the drone. We were wondering whether the use of higher resolution would help us to better assess relationships between yield and ground cover. You see here the spatial trend that was fitted, and you see that the surface here and here looks very similar, but of course you have more detail here. In the end, this is nice, but it didn't matter too much for our aim of connecting yield to ground cover. Now, for the 19 trials in 2020 that we looked at, for which we had a decent number of ground cover estimates, at least 4, or let's say 4, with yields, we have here the results on the left. These are the genetic correlation matrices. And so you can see that when, let's say here, when you see in blue, this is a positive correlation between ground cover 1, 2, 3, 4 and yield. Here you say negative correlation between ground cover and yield. And well, the overall picture is in some trial, there is a consistent positive relationship between ground cover and yield. In others, it's mainly negative. In many trials, it's sometimes positive, sometimes negative. And in some trials, it's to a large extent about 0. And here at the right, we have the residual variance covariance matrix in which we hope not to see too much pattern, and that is usually the case. Now, if we go to the higher resolution trials, for a number of the trials, we had higher resolution images, and actually the relationships between ground cover and yield are more or less the same if we go to a higher resolution. So we don't gain a lot by, let's say, adding in more information and working at a finer resolution level inside the plots. We have a little bit erratic relationship between yield and ground cover. We also looked at the heritabilities. And if you look at, well, yield is on the vertical axis, ground cover 1, 2, 3, 4 is on the horizontal axis. And what you can see is, actually there is no clear relationship between the heritability for yield and ground cover. So it's not that early on in the growing season, we can tell from a trial with low heritability for ground cover that it will not yield well, because actually anything can happen. Here we have low heritability for ground cover at the first time point, but we can have any kind of heritability for yield at the end of the season. So yeah, maybe we might expect this, but this was the result we obtained. We also wanted to know whether the magnitude of the correlation between yield and ground cover could be explained by environmental conditions, and to a certain extent that is true. In well-watered, optimal conditions, there is a relationship with some of the environmental covariates and the correlation for yield and ground cover. But once again, we've started to look at this. It's once again, so far not so obvious. So if I summarize that, well, the ground cover is quite often genetically positively correlated to yields, but the patterns are not very consistent. And the prediction of yield from ground cover at this moment is not yet straightforward. We can do more, but I'm not that optimistic that it will become straightforward. We also didn't see a very clear relationship between the heritability for yield and ground cover. And we looked at the conditions, and okay, there, I mean, we do have some indications that favorable conditions lead to particular, well, correlation between yield and ground cover, and unfavorable conditions, well, actually will break this correlation down. We didn't get extra information from high resolution, but once again, I mean, we can do better in terms of constructing predictive functions, but I don't think this will help us too much. And final slide, I think it's very important to have a flexible modeling framework for your longitudinal data. And as I said, we have been working, especially Diana Valencia, sorry. She's doing a thesis with myself and Cote Rodriguez Alvarez. And well, this is a hierarchical approach. We fit a general curve to a particular management situation or environment. Then we fit phenotypic deviations from that general condition with confidence intervals, confidence bands. And finally, we can also fit on top of the genotypes, we can fit individual plant deviation from the genotype. So this is a 3-layer spline that allows us to fit this kind of versatile functions for populations of genotypes in phenotyping platforms. And that was my talk. Anyone there still? I don't hear anything.
Is there any question? So thanks, Fred, for the presentation.
Okay.
Is there any question? Yeah.
One thing, I have less than 1 minute on my Zoom, tells my Zoom. So if things are fading out, then I don't know, because either of my Zoom subscription or yours.
So we are sorry for this small technical problem, and we'll move on to the next presentation from Raffaele Casa on the phenotyping applications and needs for precision and digital agriculture applications.
Okay, good afternoon, everybody. I would like, first of all, to thank very much Benoît Desolin and all the other colleagues for inviting me and giving me the opportunity to learn a lot about phenotyping, because I have to confess, I don't work on phenotyping, at least maybe I don't know, but maybe I could learn a little bit more. So I'm not doing really a scientific or technical presentation, but it's more on the consideration of what could be the application and needs of a downstream part of the phenotyping in precision agriculture. So you might know that by precision agriculture we mean basically taking into account much more the variability in time and space of crops across the big fields, and then to act to take this into account. So there is actually many aspects of precision land management, and it has anyway an aim of improving the efficiency, and so it's aiming towards more sustainability. So there is not really a technologically driven approach only. It's also, I mean, some other aspects. And many people talk about agriculture 4.0, precision farming and digital agriculture. So basically, why it's because usually it's considered that the different steps of development of agriculture, going from mechanization, green revolution, precision farming, and lastly, digital agriculture, in which there is much more use of automated process and robotics and decision support systems as compared to previous aspects. So the typical workflow in precision agriculture would be to get some data, get some information from the different platforms, so both satellites, drones, and also proximal sensors mounted on tractors, on implements. And then basically, most of the times, we develop what is called prescription maps, in which we indicate how to differentiate the application of inputs in basically like sowing, fertilizer, spraying, and so on. And in that, agronomic knowledge shows it's not completely automated process. Always there must be an interpretation by some experts on how to do this best. Up to now, so it's been like that. So there is actually this picture from a work I reviewed that was comparing the needs of phenotyping, the difference in needs between classical phenotyping, which is most for breeding, but also for agronomical treatments comparison, and the application in precision agriculture. So I would say that the most striking differences are that in classical phenotyping for breeding, you don't need really an instant feedback. So you can collect the data and then you can process. Of course, we've seen here in the workshop many ways of speeding up and processing of the data, but still, I mean, you don't need to manage immediately. You don't have to get a management suggestion or advice and to apply that in the field, of course. Of course, then there is a difference that they're working on small plots, so you really need the high resolution. So we've seen in many most the applications in, except the work from Marie and Minja that were mentioned in satellites. Otherwise, mostly ground-based, or so really need a small plots. Otherwise, in precision agriculture, you're dealing with larger fields, so it's less perhaps a constraint. And another aspect I would say is that the challenge of detecting, because you can derive traits, as we've seen from phenotyping, but the thing is that the traits, the variation in the traits can depend on multiple factors. So one important thing in precision agriculture would be to understand what is the factor causing the variation in the traits. So it's something that you need to understand to discriminate these things. And another aspect, of course, in precision agriculture is the cost, because everything has to be applied, so it must be cost effective, and it's about more or less an idea of what could be the cost per hectare using the different platform based on some personal surveys that I did and some personal experience about, for example, drones. You see are quite high, the cost, if you take into account. I mean, this was based on the cost of actual service provider companies coming and taking pictures, and so it's not so. Maybe it's going down. Maybe the farmers are getting their own drones and so on. So it's probably going very fast down. It's already been mentioned that there is the possibility of using very high spatial and temporal resolution satellites, and some examples like Marie also has been shown. So in theory, there is access on, and even with the very high revisit capability of daily or even. But the problem is that at the moment the business model of these private providers, is not really suitable for precision agriculture application because of the cost, very high cost. Because the cost per hectare would be low, but there is a limit there is a minimum amount which limits really the usefulness of this data up to now. So maybe it could change in the future. So concerning the constraints for precision agriculture of the different options of the different platforms, that's something that's been already shown, so I will not go too much in detail. The only thing is maybe that some satellite products, most of the times, increasingly, are offered as already ready products, so standardized products, and sometimes level 3 or even going to level 4 by physical variables and so on, whereas drones, you need a lot of still, it's not standardized, so a lot of processing that it's been carried out by the company, so that's why it also increases the cost per hectare. Then going to the agronomic requirement. So the agronomic requirement, they change according to the agronomic operation. So for example, for fertilization, especially for nitrogen fertilization, we really need a very high timeliness and to get the image at the right time and with a very high spectral resolution, I would say, but less spatial resolution, because you have to consider that then you are going to apply the fertilizer with a fertilizer spreader, which has maybe a size of a spreading of 10, 20 meters, so you really don't need a drone, perhaps, data to use this kind of thing. Instead, for disease and pest management, you're talking about diseases and pests which affect small areas of the field, and so you really need a very high resolution. Also the same for weed management. Not for irrigation, you need a high frequency, but less maybe high spatial resolution, and so on. Also for sowing and for tillage, you really don't need a very high spatial resolution, I would say. Then combining these things, more or less the status of the application of the different sensing platform in precision agriculture, I picture like that, so showing by a tractor when it's operational, so there is already commercial services which are providing this kind of service, so they exist, for example, for fertilization for a number of years. They've been existing in France, but now a lot of platforms are available. For also proximal sensors, they do already exist for fertilization. For disease and pest management, I picture with a microscope, there's many studies, but not really operational services yet provided in this field. They are a bit difficult, especially perhaps with satellites. Maybe it's not possible, and then it's going towards in weed management. We'll see that there is some operational possibility with using proximal sensors. Also in irrigation, there are satellite services already doing this, also for sowing. So, for example, I was amazed to see this example in a farm. I've been in the north of Italy. They are growing basil. You know, in Italy it's important, basil for the pesto sauce. They grow in 300 hectares or more of basil, and last year they were testing this system, which is for weed spraying based on artificial intelligence, based on deep learning. And actually, it's a French company, Carbon B, that is producing this. And they told me that they bought the machine. So apparently they're happy. So it means, I mean, this is really an operational application of the techniques maybe I've shown in this workshop. And another thing is, I think it's important to be able to try to be able to discriminate different stresses, as I said before. So there is some expectation of hyperspectral data that become easily and cheaply available, or possibly freely available to everyone. And in this context, there was the launch of the Italian Prisma satellite, which is it was up to recently the only new generation hyperspectral satellite. But lastly, also the German one, NMAP, was launched. And they have, as you see, hundreds of bands, but they have a hyperspectral resolution of 30 meters. Actually, Prisma also has a 5-meter panchromatic sensor. And in fact, one of the problems of the application of precision agriculture, of course, is the spatial resolution that's needed. So, I mean, there's some investigation going on, some projects that we have in trying to, in a way, downscale the panchromatic the hyperspectral image to the panchromatic band to a 5-meter resolution, and of course it's not easy because the panchromatic band is not covering the whole spectrum. So there must be some other hyper sharpening technique that some colleagues are developing and trying to use this. And so the Prisma can be used for estimation of biophysical variables, and like, for example, using a so-called hybrid approach, which is basically what Fred and Marie have been developing since many years. And so using simulation with a ProSail model, and then application of some machine learning algorithm. And what I think it's useful about also from what we've seen in these days is that there is a need for more suitable radiator transfer model for heterogeneous crops like tree crops and row crops. So we've seen some application also today about using 3D models. So I think it's very possible fallout from the phenotyping research that we've seen these days. So it will be very interesting. So we've been trying to use Prisma data to estimate leaf chlorophyll content. It's not very easy. So you see some scatter in the results, maybe some outliers based on the previous presentation, but also because it's a leaf level test. But of course the opportunity is to estimate many more biophysical variables like some other pigments, carotenoids and so on, and protein, and so there's many tests going on about this using this satellite hyperspectral data. Another aspect that we are investigating, and I think it's also linked with the fact of trying to distinguish the different factors or stress factors, is to identify the influence of soil, because there is also, you know, always the fact that there is variability in the soil, and it can be, I mean, hyperspectral data have been proposed to be used also for estimating soil properties, because there are some known properties that are affecting the spectra, so-called chromophores, like soil texture, soil organic matter, and so on. And this is, of course, is based on the observation of bare soil, and you have to have the strong assumption that there is a homogeneity in the first, say, 20-30 meters of soil, because otherwise what you can observe from remote sensing is just the surface. But we assume that with the tillage operation, there's a mixing of the first layers of soil, so we can consider that it's more or less does not change very much, but that's not always true. Then there is always the strong influence of soil moisture on the soil spectra, or in the soil spectra. So these are some attempts that we've been doing to estimate soil properties from bare soil Prisma data and compare with the ground truth map of ground sampling, and the results sometimes are not too bad. And also we also tested the pan-sharpened data, so the 5 meters data for the estimation of clay. We compare that with the Sentinel-2 data, and apparently the results for Prisma are quite good, better than Prisma for clay, and also for sand. So there's some work going on this. And of course, this is again for trying to have some information about the soil spatial variability in a very cheap, very economic way, because we are doing a lot of analysis. Coming to digital agriculture is especially associated with the so-called decision support system. So I got in touch with one of the leading providers of decision support systems in Italy, which is Orta, which is a spin-off of the Università of Piacenza, because they have really a large number of decision support systems that they are providing commercially to farmers, and they are very I would say, maybe aggressive in the policy, so they are really pushing a lot for this decision support system. And I was interested because of the data of the, the clients they have, the users base that they have, and also by the fact that they have a lot of field experiments going on, because basically the core of these decision support systems, their core business, I would say, is plant disease models that are even quite complex, so that really are based on the process-based description of the cycles of the pathogen and the interaction with the plants, and of course are driven by weather data. In fact, they are also marketing their own weather sensor and so on. So it's like that. And the thing is that, of course, to be reliable, these models, they need to be validated. So they, as the company, they provide they advertise the fact that these models are validated. So I looked at a little bit to these things, and basically the validation, for example, of this on a grape disease is basically done visually, by visual estimation. So the trials are visual estimations, really not much real phenotyping. There is also a lot of emphasis on wheat models, because Horta has the backing, a strong backing from the big pasta company in Italy that you might know. And these models are both plant disease models, so that provides some advice to the farmers on the risk of incidence of these diseases. And there is also, of course, a phenological component, so because there is also part on fertilization advice, water balance, and so on, so there is a phenology model going on. So I was asking the guys from Horta about the test, the validation, the calibration, because they claim to do a lot of validation and calibration of these models. They have 3 experimental farms, more than 12,000 elementary plots. And so I was really thinking that they were doing a lot of phenotyping, but they told me that basically they're doing classical phenotyping, so it means manual measurements, mostly manual measurements. They are using some measurements from Green Seeker to collect NDVI, some RGB photos, also from drone to estimate density of soil and biomass. They detect several traits, say from percentage emergence and also quality of the grain, so W1P morphological quality of the grain, nitrogen uptake, so a lot of traits that, and it's really work intensive with just a little use of instruments, so not really much phenotyping in this, although it could be very easy. For example, even now, we've seen that there is now deep learning, but even using image processing, some estimate of plant counting can be done. So I would conclude just my general consideration that there are the main constraints for adoption of phenotyping in precision agriculture is basically, I would say, the cost of the equipment. For example, I was talking to another company, service provider. They told me they have these models as well, but they don't really do a proper calibration with field plots. Like, for example, Horta, they base their own calibration on feedback from the users. So the farmers, for example, is recording the phenological stage and sending it back from an app, and then they are using this data in machine learning to calibrate the model. So that's really visual observation. So there is, I think, a lot of scope of that. Then there are, I think, good opportunities of fallout of phenotyping of the research that we've seen these days into precision agriculture, as I said, like for example, 3D model development and abiotic and biotic stress discrimination. There is also need of low-cost, maybe soil phenotyping, because soil is one of the key of a spatial variation in plant phenotyping. And of course, in digital agriculture, the need of massive adoption of phenotyping tools, because of course, this model need to be, these decision support systems need to be credible. So the only way, I think, it's really to have a serious and well done calibration, so a lot of scope for using phenotyping tools in this kind of work. Okay, thank you.
Thanks, Raffaele. Is there any question?
Thanks, Raphael, for your presentation. I think the characterization of the soil is very important for many applications, including phenotyping for breeding. And this was not too much addressed during this workshop, and so that's very interesting. But when you are going to, let's say, farmers' fields, I guess in the close future, the no-tillage techniques will come. And what do you think about the applicability of those techniques when the soil will not be bare?
Yeah, no, it's true. It's one of the constraints, of course, that the soil has to be tilled with the expansion, because I mean there is even in some so-called conservation tillage practices, some part of the soil surface is exposed, although not in the no-tillage. No-tillage is basically completely covered by crop residues. But in like minimum tillage, for example, there is it's also a practice of conservation tillage, but there is, of course, presence of crop residues on the soil, but you still see some bare soil. So I think in that case, of course, the approach must change, because maybe you have to adopt some technique, maybe spectral unmixing or something like that, to separate the signal from the crop residues from the signal of the bare soil. That's the only way, because otherwise you really need the bare soil, I think.
Okay, we have time for one last question.
Thank you, Raphael. Very nice talk. I have a question regarding tree crops and how some of these precision agriculture principles, especially based on satellite and so on, if you have any experience, how do you see that happening in the future? Yeah, what is the outlook for tree crops in terms of precision agriculture?
Actually, at the moment, at least in Italy, concerning tree crops, the most important crops in which precision agriculture is applied is vineyards, because of the high value of the wine making. So, and for that, up to now, most applications that are perhaps used are drone-based, because of the fact that you can, they sometimes, I've seen the companies, they sometimes, for example, they separate the background from the rows of the vine and this kind of application. But they have, perhaps the application with satellite data are much more, I don't know, it's really complicated, because even, sometimes they have vineyards in which they work the soil every other row. So there is one inter-row which is tilled, and another row in which there is a grass. So in the satellite data, you mix everything, and so it's really complex. I don't know how it could be possible, at least with Sentinel data. Maybe with very high resolution satellites, maybe you can obtain a similar degree of the high spatial resolution like the drone, and then separate these things, because otherwise it's very difficult, I think.
Okay, thank you, Raffaele. So now we are happy to welcome Marie-claude Mauro from Tennessee to present their work on real-time grape quality assessment.
So my name is Marie-claude Mauro. I come from the Champagne area, and I work for a champagne company whose name is Moët & Chandon, and that belongs to the Moët & C group, that belongs to the LVMH group. So the purpose of this afternoon for me is to express, in fact, the point of view of a grape harvest manager that has to manage a great vineyards. It's about 1,050 hectares, and we have to manage that to produce different style of champagne. As you see the brand here, Dom Pérignon, Moët & Chandon, Mercier, Renard, maybe some of you know some of these names. And to support the excellence of these vineyards, we start with the approach of artificial intelligence some years ago with the iPhone company. So that's what I will present today. So the purpose is much a subject of grape quality, of course, even if we have different style of wine. At the center of all these subjects, there is a grape quality. In the Champagne area, we have red, black grapes and white grapes, and only 3 major varieties of grapes. That means that the harvest time is in general very short, and we have in our company 2 or 3 weeks maximum to make the harvest of these thousands of hectares of grapes. So it's for the manager, logistic subject, transport subject of grapes, and of course management of the quality in this logistic context. So in mind there is a lot of logistic questions. So to help in this work, I start with this use case that we start to work with is the case of the grape mold. So grape mold is a disease caused by the botrytis cinerea, and in Champagne area we have sometimes rains a few days before harvest, so it can happen that we have this kind of fungus that develop on the grapes, as you can see on this picture. So actually there is different way to manage this, and we start maybe 4 or 5 weeks before harvest. We go in the plot and we count the grapes, we observe the grapes, and we select already the plots, not only on botrytis but also on maturity. The complexity is always to manage maturity versus development of disease. So we have visual observation, but it's subjective. Even for experts, we can see that from an expert to another it could be very different. And the other way is sampling, analysis, chemical analysis, but it takes time. So how we can improve that with artificial intelligence? That's the work we start 3 or 4 years ago now, and the global approach is separate in different steps. Maybe we know we talk a lot about image capture, and for us it was really new approach, and we had a lot of things to learn about this kind of approach in terms of what sensor we use, what's the quality of image we need to have to manage that. And the second step is the development of an algorithm. So we have always in mind the case of grey mold, but in parallel of that, we always think about evolution of maturity of the grapes. And the most important for us was to think since beginning to how to operate these technologies in the industrial conditions. So let's see first the first point, image capture and quality of this image, which was the first point. So when we work with the company, with IFN, we had some months to work to find the good condition in harvest time to get the right lighting and to get good condition to be able to reproduce this capture and this quality of image. So as we can see here, for example, this is a basket harvest of white grapes, and the pictures were taken at that time along the chain that transport the basket to the press machine that will produce the juice for the champagne. And we find the way, the conditions to get always the same quality of pictures. Same on another example of black grapes. And it is on this kind of image that we start all the job of labeling and to recognize and make box around the infection, the grapes infected by the gray mold, and to train the model and to get the good algorithm to be able to recognize then with the algorithm the disease. The technique is about deep learning, and we start, as I said before, the cooperation with IFN 3 years ago. It was in 2019, and we work on the basket I showed before, and we analyze each of this basket. So we had the set at the beginning of 100 pictures, 100 basket. We take the picture, and in parallel we get the analysis of all this basket to measure the intensity of the development of the gray mold in all this basket. So we were able to predict at the time the value of test that we had is an immunokit that revealed the presence of botrytis on all these baskets. And in 2020, 2021, we still work because we had more and more pictures of this basket, and we improve the algorithm to obtain first with these different pictures. So that's an example of how it works. We see here the boxes and the way the algorithm recognize all these small spot of infection and presence of the botrytis on the infection of the disease. And how all the work to finally in parallel of all these analyses and for each of these boxes to predict a value which is an index that can predict the value that we will obtain if we were doing analysis with the immunokit for a detection of botrytis. So this is all this work. And just to show you here, in 2020, the result that we obtained in one of our press center. So here you have the comparison, the relation between the result obtained with the result obtained for each plot with the result on the analytic chemical analysis, and on this way the result with the prediction by the algorithm. So pretty good result, but we try to see what happens in the real condition and how we can illustrate that those results. So here you see two examples. On the left, it represents a batch of this little basket. So what we call a batch is in fact a mar, let's say focus on different baskets, and in general there is a 250 baskets to make a batch. So this is the small rectangle that you see here. Each rectangle is a basket, and all this is what we call a batch, a MAR, that constitute the juice for the winery. So for example, in this batch, we had the value of 3, and here is example of one of these basket where the value also is 3, so it's a really good quality. And on the right, another example, another batch, the result we get, the value that you predict was 54, and one example of one basket is 83. So all these results helps us to see that there is differences, of course, in the value, and also differences in the repartition of all those boxes that we assemble in the different batches. And when we see that, we say, why? Here we have very good basket, but we mixed with a basket where it will have put aside if we had the result in real time. So how we can manage the real time with all these boxes in the real industrial condition. That's the point. We had good algorithm, we get good result, but now the challenge is how to manage that during harvest time and in real time processing. This picture to give you an idea what is an industrial press center. So in this center, for example, we press about 500 to 600,000 kilos per day. So still this problematics of logistic, of rapidity to manage all this basket to get good quality. There is time also challenge in this condition. So when you arrive here and you say to the people, now we are going to manage the quality, we are going to set batches of different quality, and we are going to take pictures of boxes. They say, you're crazy. We have something else to do than taking picture of each of this basket. So the challenge here, what we had in this harvest in 2021, is in fact to find the good condition and the way to get this image capture in this condition, always in control condition to get standard image. And also the challenge was to get result in less than 10 seconds, because we cannot stop all the things and say, wait a minute, we need to take the picture and we give you the results later. And also the way to establish these different bench, different qualities of batches. So what we did in fact is that we take as a unit the palette. When we go in the vineyards and we pick up the grapes, when you go to the grape center, in fact the unit is a palette. So the palette is here. It's 12 boxes. And we decide to take the picture of the palette, in fact, and to take the picture of the 4 boxes that were on the top of the palette, and to use this unit as a unit to make the different batches of different qualities of grapes. So this is the system. So this is not a mobile system. In fact, this is the person here on the forklift that comes to the cabin. The person takes the picture, and on the screen there is a light green or red that says this is good quality or this is a less quality. And according to this result, the person on the forklift goes to the batch 1 or to the batch 2 to constitute the batches of different qualities. So that's what we've done during harvest 2021, and that way we valid the fact that it could be that this capture, this image could be used in an industrial condition. And here is an example of these different batches. So here you have a number of batches. So in all this case, it's 12,000 kilos of grapes juice. And the result that interests the enologist here is, in fact, nowadays, the result with the gluconic acid. That's the result on the juice. So when the juice arrives in the winery, they analyze this gluconic acid, and they very easily say this kind of result, this kind of batches, has to be set apart because they have lesser quality. And what we have in our press center is the result with, on the red line, the result we obtain with the pitchers. So we have still to work with IFN to get a better scale, to get also higher differences between all these batches, to easily put apart different quality, maybe 2 or 3 quality different, and to get good difference. But we can see that this year already we were able with these batches to separate, for example, here 3 batches that were of lesser quality, instead of having all these batches of quality, an average quality. So what is the next step? We would like to organize in a better way the capture of all this palette. So we start to study with the company, with IFN, to optimize the size, to be able to put 2, 3, or 4 of this cabin in the press center. This year we valid with only 1 cabin, but in the next step, for the next harvest, we will have probably more cabin in our press center, and also to integrate it in the operational flow, so to be more fluid in the use of this cabin. So in fact, we will extend the project in 2 other press centers. So in the press center we use this year, and in 2022 we will have 2 other press centers. So what is the next step? We can now imagine a different way of using this kind of features and this kind of technologies in our way of managing the quality of the grapes. Of course, we think about new algorithms, not only for degradation. First was botrytis, the case of botrytis, which comes very suddenly during harvest. So we need really to have a way to evaluate this disease. But there is other disease maybe we can tomorrow manage like this. And more interesting and maybe more difficult is to also optimize all the aspects of maturity, because we always checked with chemical analysis the quality of grapes and the maturity of grapes, but maybe we can go further and make batches still more homogeneous when we can do it really on each pallet, when just the pallet arrives at the press center and not the result of 2 or 3 days before. So it could be probably good to homogenize the quality of the grapes and of the harvest. And another aspect, maybe more long-term aspect when we can study and develop, is the way we can use this kind of pictures. Is it only to set apart a different grape quality, or is it to improve the quality, and especially, as I said before, with maturity, maybe we can go to premium aspect of maturity and to make really premium batches of grapes that can be used for the Grand Cuvée, and to select really this kind of grapes very quickly and very close to the vineyards, and not to wait degustation and all the things after fermentation to decide of the quality of these grapes. And the other point for the future is probably to extend this to the press center of our partners, because here I talk about vineyards, our vineyards, but we also buy grapes in different vineyards. And we work with 400 partners in the vineyards that press the grapes for us, that we buy these grapes and they press the grape for us. So maybe tomorrow we can give them the same procedure, and to decide to make the batches of different qualities of grapes right during harvest at the press center. And why not? Maybe it's a dream for now, but maybe tomorrow do it in the plot, to have a small system to be able to take the right decision, to look at the grapes in the plot and decide if it's the right date or the right moment to pick the grapes. That's really a big decision and a big challenge for the people, for the managers that decide the harvest, is to decide the date we picked this plot or another plot before, or so on. All the planning of the harvest is really a challenge for those people. Well, thank you for your attention, and thanks to the organizer for the invitation.
So. Thank you, Marie-Claude. So, is there any questions? Yes.
Yes, thank you for the presentation. So, when you take pictures of the surface of the tray. Yeah. How representative is that? Because you might have all the botrytis grapes in the bottom. So, did you check that?
Yeah. This is the question, the first question that was asked. And at the beginning, in fact, as we worked the model on the boxes, we said how to manage this on the press center. But this was really no way. So we had to think differently. And when we decided to make the picture on the 4 boxes on the palette, in fact, we had always, still in this press center where we studied that, the convoyeur that has a system to take a picture on each box. So we can make the correlation between, if we take the pictures of all the boxes of this batch, and if we compare to the picture that we take on the palette, is there really a good relation or no relation? That's the work we are doing now, and it seems that the correlation is not so bad. So it's not 100%, but if it is even 800%, it's okay. I think we improve the system.
So, question regarding the model. So, is the model capturing the surface of the botrytis, or it's just an inference of the picture itself? So, how did you label the picture? Is that was it a value?
It's an answer for Alexis or Jérémy.
Yeah. So. The model used for this application is we just use boxes around the botrytis spots. So why boxes and not segmentation? Because here it's a real industrial application, and we need to monitor this during the acquisition and during the harvest. So. As we saw this morning with the presentation, we'll always have new cases that will make in default the deep learning. So we need to be really fast to retrain the model during the harvest time. So there is really kind of trade-off between the accuracy that we have and our ability to monitor and to be sure that we are able in real time to monitor and to improve the model. So that's why we choose like a simple approach, just a bounding box around the botrytis spot. And then there is another, so we just use deep learning to extract some descriptors on the image, and then we simplify those descriptors in one botrytis index. But just bounding box around. Sometimes the simplest things are easier to maintain in real world application.
And so did you test regression? So deep learning with regression instead on the picture?
So directly image from the okay. So the idea, so we didn't try this directly. Why? Because to train this, we need a lot of to make this, you need to have a lot of images and a lot of so as the ground truth is chemical measurements that is really hard to obtain. So first, it's really easy to have good deep learning models just to have bounding box, because we can make this robust because we have the image, and with our eye we can label the data. But then to make the link between the image descriptors and the botrytis index, it's really hard to have ground truth. So we use another model, like a simple machine learning models that needed really less points, 100, 200 points, and so it's the approach. So first we just extract descriptors, and then we match a second model between the descriptors and the botrytis index. So it's just because we lack of ground truth, so regression was not possible.
Thank you.
You want to? The last one.
It's just one question. So now you will have a lot of information from the end of the story, so from the final quality of your grape. So do you think it's also interesting to go back to the production practices or things, or is there a way to have a feedback to the producers to enhance the practices from the final quality?
Yes, this can be first application will be to work with our partners where we buy the grapes, to at least say during harvest this is good quality or not quality. But if we, I think, want to go to the plot and to work really further on the quality of the grapes, we need to probably have an image of vineyards. As in our organization, and even in Champagne organization, we always harvest a plot. We decide the date with plot, but probably there is difference of quality because of exposition, because we are at the top of a coteau, or you are on the other side of the coteau, and maybe tomorrow the way will be to pick up not only plots, but to pick up the grapes because of the vigor of grapes that are different between the top or between different aspects of exposition of the coteau. So I think the approach with like we see with the satellite in the vineyards to see the vigor could be a next step to be before this time of harvest, and to try to work on the vineyards and on the quality of maturity and so on in the vineyard.
Okay, thank you, Marie-Claude. So now I welcome Eric Duchêne. So we still stay in the vineyard, but now we will be in the field.
Yes, we are going to continue to speak about grapes, and I think the answer of Marie-Claude, the last answer, speaking about vigor, is completely in the scope of what I'm going to present. How does it work? Non, j'ai fait une bêtise. So we are going to speak about the genetic variability of grapevine vigor parameters as described with liDAR data on associated quantitative trait loci. So I will speak about QTL in the future, but QTL stands for quantitative trait locus, in fact. And what is this? It is a part of the genome that is responsible for a variation in the phenotypic traits. I didn't touch anything. Okay. So in fact, this presentation is a talk that Elsa Schedid, who is a PhD I'm supervising, presented a few weeks ago during a congress dedicated to grapevine. But I would like to really thank people from the CAPTE team, especially Frederic, who introduced us in this system. We benefit of all the work that has been done in the phenome program, and you will see that it was very important for us not to start from scratch, but to use what was already available. I also have to thank Raúl López Lozano and Maxime Soma, who helped me with all what is about algorithm to analyze the results and to extract the data from the files, etc. So what is the context? In fact, we are not really breeders. Yes, we are breeders in Colmar. We are quite a small team. But our objective is to propose to vine growers some new varieties that would not need any spray of fungicide. Okay, so we have some sources of resistance to powdery and downy mildew, which are the two major diseases in grapevine, and we have research programs aiming at finding the molecular markers that we can use in breeding programs to select those resistant varieties. But we also have breeding programs. So we have a research program and breeding program all together in the field. So we have thousands of genotypes in the greenhouse and in the field. I am responsible in this team of what is linked to grapevine quality. Grapevine quality is sugar content, acidity, aromas. Okay, and I will continue. Okay. So we have some objectives to understand how quality is constructed in the vineyard. Why we have differences among genotypes for acidity or for sugar content, for example. And to explain sugar content, leaf area is one of the main points, because leaf area determines photosynthesis, sugar accumulation. And if we have also the yield level, we can calculate the fruit to leaf ratio, and we can correlate it to sugar content. So to estimate leaf area, or more generally vine vigor, we use leaf area techniques I will show you later, and pruning weight, which is quite easy. You just have to cut the shoots and just to weigh them with a scale, and we use these traits. Usually we do this by hand. I will show you how we take picture, or we weight the wood. And it is very labor intensive, time consuming, and sometimes we have some subjective estimates. So we have a lot of work to do in estimating the traits for new genotypes. And you have to, presently now all over France, there are more than 2,600 new genotypes under evaluation for the resistant to disease. So just to give you an overview of how important it is to have some new methods, rapid methods to characterize all these genotypes. So we tested a liDAR system for the evaluation of leaf area and pruning weight of grape vine hybrids, and we detected quantitative trait loci with this data. This is a picture from my window, in fact. This is, okay, from my window with the Vosges. We are in Alsace, in the north of France. And we use the progeny from two parents, IG119 and Divona. And they carry different resistant genes to powdery and downy mildew. And I will not go into details for these genes. We have a population that we call 50025, where we have 250 genotypes. Among these 250 genotypes, 209 of them are planted in this vineyard. We also have the parents, so these two, and a control, which is a Chardonnay. We have, for each elementary plot, we have these genotypes, the parents of the control. Each elementary plot is constituted by 3 plants, and we have two blocks, which means we have something like 440 elementary plots to characterize in this experiment. The first thing, I will go quickly with this slide, because we need to have some genetic information about all this population. And what we use is genotyping by sequencing, which means that we take some samples from all the genotypes. We have a digestion protocol. We add some code barcodes. We have some PCR parameters. And we pull all together 96 genotypes in the same tube. Okay? And for all the population, we sent three tubes to a sequencing platform, and we have 3 FASTA files, not FASTA, but text files, in fact. And then we have a lot of bioinformatics, demultiplexing, creaming, alignment on the reference genome, filtration, variant call. What we are interested is where are the variations in the genome for each of these genotypes. And with all this data, what we have is what we call genetic maps. Okay? We are quite satisfied with this result. Okay. Oh, it doesn't work. Back, please. Please. Okay. So we have a very nice genetic maps. We have what we call parental genetic maps, one for Divona, the other one for IG119. For each of this map, we have more than about 20,000 markers with a very, very high density of markers. And with this information, we can build what we call a consensus map, which is kind of synthesis of the two parental maps. Just you don't have any important information in this figure, just that we can find only with genetic distance the 19 pairs of chromosomes of the grapevine, with a very low resolution, which is 0.1 centimorgan. Regarding phenotyping, what we have is this kind of equipment, which is basically the same as on the large phenomobile in the other plot in France, used for annual crops. So we have a GPS system, or RTK GPS system. We get the position of the mast, in fact, at a precision of about 1 centimeter. We have here a control unit with a computer that can send some orders to the cameras and LiDARs to stop and start data acquisition. And there is also a hard disk to store all the data. And the driver can supervise all what is happening with a tablet in front of him. What do we have in the measuring heads? We have two types of instruments. We have a RGB camera, and I will not speak later about the data we have with the camera, but we have also a SIC LiDAR with a high frequency of acquisition. And what can we do with this? We can generate this kind of point cloud. This is a raw point cloud. We have two LiDARs, one at the top, one at the bottom, because our grapevine are quite high, are 2 meters high, so we need two LiDARs. And we cannot do anything with this kind of raw point cloud. So we have to remove the second row, we have to remove the soil. And for this, we developed some scripts to generate this kind of simpler point cloud with only 3 plants. This is for one genotype. And we remove the soil, we remove the background, we remove the outliers. And this point cloud is also based on voxels. For pruning weight, for example, we use 5 millimeters voxels. And for the canopy itself, we use 1 centimeter voxels. Okay? And what the simple metric we use with this kind of data is just the number of voxels with at least 1 impact. Okay? And we converted the number of voxels in liters. Knowing the volume of each voxel, we just multiply the number of voxels by the volume of each voxel, and we have liters per genotypes, in fact. This is quite simple. And this was for the LiDAR, and for the exposed leaf area, we use this kind of system for a long time now. We have a blue curtain. We have someone carrying the blue curtain, and we have someone else taking pictures. Okay, and then we just use an image script to extract the green pixels from these photos, and the statistic is the coverage fraction of canopy covering the whole scene, and then we can calculate what we call exposed leaf area in a meter per genotype, in square meter per genotype. This is exactly the same plot with the LiDAR system, so we can see we can still make some improvement, but here are the wires that we have in the vineyard, and they are not straight. This is because our system is not stabilized, you know, the mass is moving. So we are now working with IMUs to correct the point clouds in order to have a straight line for the wires. And we use the same metrics as for pruning wood, which is the number of voxels with at least 1 impact in the point cloud. We were quite happy with the correlation between the apparent volume at veraison. Veraison is the moment where the grapes start to ripen. Okay, and this is the apparent volume is obtained with the LiDAR data, and here we have the exposed area obtained with the pictures, and we are quite happy with the correlation with R2 about 0.9. I have to explain this kind of graph because this is how we are interested in. Here we have the chromosomes with the density of marker, chromosome 1, chromosome 10. And here we have what is called a load score. I will not go into detail, but the load score is the likelihood of an effect of a point of the genome. Okay? And we have a threshold that we calculate thanks to permutation, 1,000 permutation. And once we have some part of the curve above this threshold, we can decide this part of the genome has an effect on the trait. Here is the exposed leaf area, and with the LiDAR data, we have better results. Okay? We have better QTLs with higher load scores on chromosome 1, on chromosome 10. For pruning wood, what we did, we took some LiDAR data before pruning and after pruning, and here we use the number of voxels that disappeared between the two datasets. Okay, and we converted them into volumes in liters. And the correlation is not so good with the apparent wood volume in liters on the pruning weight, but it is not the same thing. because from one hand you have a volume, on the other hand you have a weight, and we have checked that the wood density can be different from one genotype to another. So it's quite normal that the correlation is not good, however still correct. And same graph as previously, we have for the pruning weight, we have 1, 2, 3 QTLs, and when we use the liDAR data, we have 5 QTLs, stronger QTLs. So we are very happy to enhance our QTL detection with the liDAR. And I'm very, very happy because here we have the largest or the stronger QTL on chromosome 1. We have also a QTL for sugar content at the same position, which means that we can explain some part of the variation of sugar content with the liDAR data. So we are quite happy with the system. Okay. So the proposed high throughput methodology based on liDAR data is effective in measuring relevant growth characteristics of grapevine in the field. The main goal was to characterize the genetic variability and grapevine hybrids, and the fact that we detected several QTL for both traits validate our approach. So we are satisfied. And we can even conclude that electronic phenotyping can be more powerful and accurate for QTL detection than conventional phenotyping method. Okay, I have to thank all these people from Colmar from the CAPTE team, and also Robopec and Mika 3D who built the system. And I thank you for your attention.
So thank you for your presentation, Eric. Is there any short question?
Yeah, really nice presentation. It's good to see the liDAR in action in grapevines and goody crops. I was wondering, did you measure actual leaf area, or that was more like the weight of the area?
It's for just the weight, the surface, the number of green pixels in the scene from pictures. But we didn't try to make some destructive measurement to check everything. But I mean, maybe you can do that. But
yeah, well,
we are satisfied with this.
Sure, and it's always the question: what is the value? What is the benefit? Yeah. Whether it's the total leaf area, or actually you want some.
In fact, I would more believe, in fact, in the liDAR, because the liDAR is like light. You have an impact, whatever the number of leaves you have behind. If you make this destructive measurement, you will measure all the leaves, and I think real liDAR is more representative of the actual light interception than the true leaf area.
Yeah, absolutely.
And here.
First
yep.
you.
Yeah. Why did you choose to downsample the liDAR data using voxels?
Because the speed of the tractor is not constant. So the density of points was not homogeneous across the scene. Okay.
Thank you.
Thank you for the presentation. You presented higher lot scores, but and sometimes more QTL. But have you got the result of some QTL that you believed in that disappeared because it was linked to outliers or whatever? So can improving the quality of the measurement make QTL disappear? Because this happened to us in some cases.
I hope not. But I'm not sure, I cannot answer. Because we have some data on some other experiment. We need to put everything together to have another view on all this data. It's just a snapshot on one nice experiment.
Okay, thank you, Eric. So now we will take a short break. I will kindly ask you to come back at 35 so we can finish on time.
Okay, good afternoon. So we start the last part of the last session, and we start with a presentation from Alexis Comar. So please, we have one presentation less, but so we'll finish a little bit earlier. So please, Alexis.
Hello, everyone. So, first, I would like the organizer to inviting me to the... No. Let's get started. So now we're going to speak a little bit about what's our vision as Hyphen of how our customers seems, or at least are communicating with us, the way they're using high-throughput phenotyping data. So we're going mainly to focus on seed breeders, but not only. So yeah, so my name is Alexis Comar. I'm the CEO and founder of Hyphen, which is now 7 years old, almost 8. And yeah, it's a journey with UMT-CAPTE that started back in 2009. We work with basically any types of data, and we will really not focus on what Hyphen is doing on this talk. So yeah, so who use high-throughput phenotyping data? The first people, which I think we extensively talk during these workshops, is the academics. And academics are using data for also answering scientific questions for themselves. We've seen a use case with agro-processing, so champagne making, but we could think of all the other agro-industries making the can of beans or stuff like that. We're having seed breeders, which, and it's always a big question for me, is really the main focus of high-throughput phenotyping, and is not always where there's the most business for Hyphen. Crop protection, and finally, agro-production. We will start this talk by really focusing on seed breeders, and then we'll look a little bit at the other use cases, just to have a quick glimpse of other use cases we can have and which we work on. So, to start with, when you work with trials and seed breeders, you're having a huge diversity on types of trials. So of course you're having a lot of crops, but also you're having a huge diversity of trials. And the question is, okay, but what do they do with those trials? And I'll just go very quickly into what seed breeders do. From my understanding, I have a very limited knowledge, but basically a typical program, let's say the old-fashioned, how they did it before, was really they make a lot of crosses and lines, and their job is to ditch, to put to the garbage all those lines they made until to have a commercial cultivar after 5 to 10 years, depending on the situations. And each year they're having more seeds because their crosses are allowing them to have more seeds and seed production. So they're going to have bigger plots, then more sites, and then repetitions. And there, at the beginning, they're really in a situation which they're not able to have yield. And so there's a lot of trials where yield is not achievable. I mean, yield means nothing because it's just too small. I call that nurseries. There's other names, and we will see that today it's way more complex than that. And then there's field trials, so whether you call it preliminary yield trials, advanced yield trials, elite, etc. And there, it's really all about yield. And it always has been about yield, and it's still about yield. And then once you've chosen your varieties, you want to often to compare them with competitors. And there we're much more about what I call product evaluation. And we'll just have a glimpse of that at the end of the talk. Today, I think the game changer, at least from my perspective and for us, is really this genomic prediction. So why is it a game changer? There's the old style genomic prediction, which is I want to predict yield from my genomes. And this, well, it's still about yield. And yield is not phenotyping. Or it's the basic phenotype where Hyphen doesn't help. And now more and more it's about selecting the right parents to cross. So it's really in order to deal with the crosses you already made, and how am I going to recross that for the next selection program. And there it makes sense, because you don't have yield. It makes sense to have high throughput phenotyping in order to have this new innovative way of trying to make the most of your breeding populations. So okay, so if you try to summarize it from a hyphen perspective now, so from my perspective, basically we can already split two types of trials. Trials where yield is not achievable, and there what we do makes a lot of sense, and we can go very far into phenotyping things. And where yield is achievable, and there basically is just about correcting yield, because all the rest, they don't care. They just don't care. So when yield is not achievable, the first thing you want to try to understand is, okay, is my cross looks good or not? And can I try to be a little bit more objective than a breeder in the field that, depending on what he had last day at home, will feel more or less good mood to ditch or to save some crosses. And this is really about what I call the limiting factors and the yield components. And it's also to try to predict how those lines are going to behave. So how they're going to, what type of yield can they do in your diversity or in different environment. And we'll see a little bit about that. And when you have yield, really it's just about, actually yield is really something that is not black and white. We have a number, and no one knows if you can trust this number. And I think Fred a little bit mentioned that, Fred Van Eeuwijk in latest pitch. I will be much more brutal in the way I will say it. I mean, all the game is, can I trust the yield I'm having? Is it messing up my analysis or not? And if it's messing up my analytics, can I correct it? And we'll see that it's always highly debatable. So let's start with situations where yield is not achievable. And to be very concrete, it looks like that. You're having couples of plants, generally a line. It grows, it's not homogeneous. Sometimes you're having bad emergence. I mean, it's really diverse. It's many things. And what they want generally is just to have a rough idea of how this plant is behaving. And the first thing they want is phenological stage. Or am I having early crosses, late crosses? Can I have that in a standard way? I'm showing a basic example on sunflower. You know, they were also not at the same time. This one is already flowering. This one is not flowering. Can I have that across 10,000 lines in just one drone flight? That makes a lot of value for me. They also look for disease. So we've been doing things with disease, and it can also be rough. So this was a Sarcospora project on which we worked. ACAR project, it was where, okay, I don't think you see it very well, but there you really see that there's more disease than there. And okay, can I simply see how my cultivars, my crosses are behaving compared to diseases? Another example is early vigor. So this is even in another place with soybean. I mean, is my early vigor strong or not? And it's really simple questions. And actually, more and more now, they are, no, sorry, now I went too fast. They are adding those questions one and the other. And really the idea is to try to understand how those crosses are behaving in order either to make, I guess, some genomic prediction models based on that on crosses. I want some early things, I want some non-early things, and things that are ultimately probably going to be linked to yield, but it's way too early to be sure and to know how. I mean, then that's my point of view is, okay, how do you try to integrate the climate and all that? And my vision, and now it's more my point of view, is the way we're going to do it is really by combining those phenotypic data with environmental data. So the best example, I think, is phenological stage. What you want actually is you're combining temperature data, generally degree days, as we've seen a lot in this presentation, with an event, flowering, ear, emergence, etc. But we can think of more complex traits as well, like light absorption. So how much light am I absorbing? That's what we call Q-pore. I've seen presentation in University of Queensland. They call that RU. But we can also go a little bit further, like trying to assess how much theoretically water should the plant have transpired, and look at if the yield, not necessarily the yield there, but if the immediate stress like temperature are behaving like your water balance model is saying. So those are things we've did with some customers where we just looked at early vigor. You know, so when you're having stronger early vigor where you're making more leaves, and so normally you should transpire faster. When you're having a lower early vigor, well, you should be more conservative, but it's not always the case. And just knowing that enables you to try to highlight some processes that make sense for them to detect and to see. And so that's a little bit my small provocative questions I had to François yesterday is, okay, on all those new things of genomic prediction, is it going to happen more to well describe those processes? Are we going to do it in the field because we can scale? We can have 10,000 lines that we try, and actually the data, the scale is important, or should we have better metric that we're able to have in greenhouses with very precise systems? It's probably a mix of both. I mean, I'm not really clear on that. What I wanted to say is generally what happens, or the feeling of what is happening is people make crosses and they're really in logics of trait integrations and things like that, and then they test it in the field. I'm wondering if we shouldn't, I mean, if they're not, no, if my clients are not trying to put all this into a general workflow, and actually just going into greenhouse to check that those weird cultivars, those weird crosses, why? Yeah, and that's really, I think, the changes we will see in the coming years. Now, if we have yield, it's simple. People just want yield. I haven't been really confronted to people that were interested in other metrics than yield, except for academics. Then I want yield, but I have, and this is a true example, so that's a customer trial, but I have field like that. And the question is, can I trust my yield in a field like that, where I'm having some chlorosis deficiency, etc.? And the answer is, well, before we're just ditching the site, we're just ditching the trails, okay, I'm not trusting this trail, finished. But the question, and there I'm using another example, the question is, when I'm having such an event happening, does it really is justified to just throw my trail to the garbage, or can I still save it? So there I took an example where we went all the end, you had a lot of weeds. You had a massive amount of weeds. Weeds were poorly controlled, and when they realized it, it was way too late. And so the big question was, okay, should we stop the experiment and we stop bleeding? It's really expensive to have these types of trial, or can we still save enough data to justify the investment? And so what we did was to just quarantine all the microplots where you had too much yield, too much weeds to be able to compute what we thought would be a yield that would make sense. And actually what we realized is that it's still a lot, and it's 532 plots where you, just don't use them. But you still have a majority, 85% of them, that are having probably, weeds, where weeds were not that much in competition with your crops. And actually, we do that massively with our customers. So trying just to give you a kind of quality rating, saying, okay, this microplot looks good, this one doesn't. And sometimes, well, they have great trails. Sometimes not that good. And then they take their decisions. This is not up to us anymore. And if you're able to give those data very quickly, they can take their decision during the growing season, and they can better manage their trails at all the levels. The second thing is, okay, now that we said yield is maybe not reasonable, and we can quarantine at plot level. Can we correct it? So actually, people didn't wait high throughput phenotyping to correct their yield. No? They are doing that a lot today, and they really use special correction models. I think it's PATS. I mean, Fred Van Eeuwijk was one of the ones that has the most famous model to correct all of that. There is a little bit of research. I've seen a little bit of research with other companies trying to say, okay, should we correct from this spatial heterogeneity directly using yield, or could I use some traits that are linked to yield? So that's the first question. I'm not completely convinced about that, but it's worth mentioning. What I'm more convinced on the other hand side, and I think it's worth giving a concrete example to really say it, is this is sorghum. I'm having a hole in sorghum. I say that, okay, I lost a percentage of my harvestable area. Yes, I agree, there's compensations effect, so my yield is not going to be as trustworthy as if it was a perfect plot, but on the other hand side, I need data, I need to take my decisions, I need to go further. And do I prefer a yield that is not corrected, or do I prefer a yield where I correct from the line? So 21% of the line that misses. It's the question at the end of the day, and a lot of people are correcting it thus. And that's, you can try to generalize it. So when you're having some drought issues, by example, and you're having, or you're having a tractor that is just driving into your microplots, well, your surface is smaller, and you just can account for this loss of surface to try to have a yield which is kilograms or weight per hectares per surface. And you can try to account for it. And you can try to account for it whether it's by counting the number of plants. And once again, they can compensate, so it can be tricky sometimes. By looking at the rows, holes in the rows, or just looking at the harvestable area at the end of the day. So that's really how people on yield trials are using, at least that's my sensation, the data we're providing them. So to conclude on that, on this part where you have yield, the first thing is, I think, high throughput phenotyping, and this is a real major change. Before, you were really looking at trail level. Okay, my trail doesn't look good, my trail looks good, and all that. Now we can look at plot level. So we can look each individual plot if I think it's good or not. You can try to increase accuracy with all the limitations I really insist on, because it's not automatic, but I can try to increase my accuracy. And I can have all of this information before harvest. So if I process my data fast enough, I can have all this information before harvest, so I can take decisions on the quality of my program. And I know what is going to happen, I know where I need to focus my attention, what people need to analyze, and I don't have this chunk of data coming where I need to figure out, and I have no time, what is the good data to what is the bad data, where should I focus, etc. So that's basically what I've seen in the breeding industry. And so I'll take a couple of minutes just to tell you that we don't just work in the breeding industry. So we also, I want to speak very quickly about two other industries in which we start working. The first one is what I call crop protection, but actually we should extend it to product evaluation in general, whether, and we'll discuss that, and a little bit about agro-processing, or as well, high throughput phenotyping can make sense. So when we speak about product performance evaluation, I encompass, I mean, maybe we can change vocabulary, etc., but me, I encompass the test of chemicals products, and today it's really about biocontrol and biostimulants. That's the new product that are coming in, so it's for the environment. the test of cultivars, and more now the farming practices. So how can I combine those new products that are coming in and those new cultivars with new farming practices in a more local way? So that's what we call agroecology in France. No one knows what this definition means, and everyone says something different about agroecology. I prefer to present it this way. It's really about trying to locally adapt the way we're growing plants, depending on which cultivar to choose and which products to apply, organic or not. And for that, you're having a huge diversity of type of experiments. You can have experiments, what we call OFE, on-farm experiments. So this is really the new trend, is to say, okay, because we want to change the farming practices, it needs to be bottom-up, and so we need to make those experiments at the farmer's level. And this is really something that is gaining momentum a lot. And how do you do the high-throughput phenotyping with the farmer is really different than what we're doing with breeders, so it needs to be considered. There's a lot of CROs, so company research organizations, so there's a lot of outsourcing that is implied. I mean, it's really something that is complex, and generally the technologies, when you're into this logic, are not the same as the technologies we generally speak with breeders or academia. With breeders and academia, it's basically drones and phenomobile, wide range. There we can also have satellites, because one modality is 1 hectare or 1 field, etc. And what does it contest? What does it consist to make product evaluation? Well, for a very long time, it was just about yield as well. Okay, I'm putting a product, a new cultivar. Okay, what do I gain as yield? Oh, I have some more yield. It's efficient. And now that we're trying to use biocontrol, biostimulant, and things like that, well, they make 100 trials. It sometimes works in 30 trials. There's nothing in 50 trials. In 20 trials, actually, you're having a negative impact on yield. And does it mean that this product is not working? No. It just means that it's not always having an impact on yield. So what you want to try to understand is what are the yield components and why? In which context, in which situation is this product? Is it going to work and have a beneficial impact on yield? And in which situation is it going to have a neutral or non-positive impact on yield? And once again, why do you want that? For farming practices. And that's where high-throughput phenotyping kicks in, is that suddenly you want much more data. I mean, they already were capturing more data, but now you want much more data in a much more efficient way. And that is comparable. Okay, so what I want to say there is that this thing of product evaluation, we're not speaking much of it because it's a very, very complex ecosystem. You're having the companies that are making those products, you're having CROs. Who is making the high-throughput phenotyping? Who is pushing? How do you make your business model there? Plus, you're having a very, very strong limitation for regulation. So there's standards of EPPO. So I saw from Raffaele that some companies were just following the standards and that's it. And as long as the standards are not also going through digital phenotyping, there will be no push to adopt the technology as much as possible. And that's a little thing I would just wanted to mention for the people that are interested by that. EPPO, which is really an important organism, is starting to consider digital technology 10 years later. And is going to make a workshop on this topic I think it's in June, so next month, end of next month. And I think this means that today the adoption is slow, but it's probably going to gain momentum in the coming years. And I don't know at what pace, but I really think it's worth mentioning nonetheless. The second use case I wanted to speak is agro-processing. So there, agro-processing can be everything, making beer, making champagne, making cans, peas canned, or whatever you want. And they always have two use cases, always, always, always. It's predictions. How much am I going to make and which type of quality before harvest? And once I have my harvest, to make an assessment about how much they actually made before going and processing it. Because once you process it, I'm thinking mainly about use cases in sugar there, but different quality is not going to yield to the same customers, depending on what type of sugar you're able to make. You're not going to sell it to the same person, and so you're not going to position yourself to the same type of sales, depending on the quality. And so I would like to thank you again, Marie-claude, to have given us this example about post-harvest assessment. And so we're working on other topics as well, on predictions. And really, yield prediction is something on which is not today's talk, but is, the principles are changing on how to assess yield with those new technologies. And I really think that it's going to be way more accurate. So to conclude and to finish, now we are having a lot of sensors, and I think in this workshop we saw a lot of new technologies that are being used and a lot of new traits we are able to compute. And really, for me, the first value of digital phenotyping all the time, whatever is the use case, is to have data as fast as possible to take your decisions. So it needs to be a support management tool for the breeders, for the agro-industries, for the product development. It also enables you to have all your data stored in the same place, whatever is the database. And so that means that you're going to be able to distribute this information in timely manners to all the stakeholders of your program. And this is a little bit a game changer, because today everyone is doing things everywhere, and it takes a lot of energy to centralize all the data, and often it's never done because it's too much energy. And finally, it will allow you to look at some, to automate as well some analytics, some workflow during the season, so that when you're having your data analysts wanting to focus on which decision to make, they will always have a good indications of what is in your data set and what worth investigating and what doesn't worth investigating. Voilà. Thank you very much for your invitation.
Okay, thank you very much, Alexis, for a very interesting presentation. Are there questions?
Thanks for the presentation. I have the question, what is the best vector sensor combination for an early generation breeding nursery? Is it still a drone, or would you just recommend to have something more close to the crop in the future?
The question is always price. No, it's true, because at the end of the day, those things, you need data points, and the data points need to be cheap, and it's really about volume. Those are really questions we're asking ourselves. So in the next 3 to 6 months, we're going to work very much on trying to give options to our customers on which types of technology to use and to precisely put costs upon it. Drones, I do believe that technology will start with drones, especially high-end drones, where you can really work now and make plant by plant. We work for some customer plant by plant and sunflowers. So this is things that works. I do believe also there's a use case for phenobiles type systems. But once again, the business model is different, and I'm not sure which one the breeders will select. On working, it's really about money, I guess.
I think maybe time for a short question.
Thank you for this presentation. It was really great. Again, for the third generations. So, okay, we have the phenotype, but this is for tens of thousands of lines, I understand. So what is the next step? Are you thinking of a clustering algorithm to cluster all the lines in rubbish, perhaps, or promising? Or what is exactly what you want to do with that, or what your customer want to do with that?
What I want to do, nothing. The sensation I have, and once again, it's always, everyone has its own recipe, and often those recipes are quite secret. But the sensation I have is it's really about how to make the best process. So I'm making cross one with the others. I'm having a huge pool. Often crosses are expensive to make, and the beginning of, I mean, my understanding before this push I had to try to understand better was that actually the idea was to select faster which crosses looks promising and which crosses doesn't look promising. And what I think I understood now is that this is the old way of doing things, and the new way is to say, okay, actually we don't want to make too much crosses. So we want to try to cross the right parents together and not to cross the things that will not work. So that's my understanding. But once again, it's an understanding, and I have a feeling all of it is about recipes, and everyone has a different recipe in order to make it work.
But then there's a follow-up question. If you are actually looking into what crosses are best, and you're in the crossing block, and then again the question is if the breeders want to have more information about the phenotype than just yield.
They can, I mean, the situations where I have a sensation we're gaining momentum is when yield means nothing. You just don't have enough seeds to have meaningful yield. Because once you have yield, it's really what I said. Once you're able to achieve yield, forget about everything else. I mean, today, maybe they're wrong, but today it's about yield. So all those users is when they, for any reasons, which I don't necessarily always understand, they're not able to achieve yield. Because I agree with you, once they are achieving yield.
I mean, they would actually need the yield to train the phenotype, actually. I mean, they would have to...
Well, I have a feeling that they are trying to train it on other desired traits. But maybe, I mean, once again, it's a feeling I have.
Okay, we are a bit short of time. I mean, it's already maybe time for the next presentation. Sorry, maybe you can discuss afterwards. So it's time for the presentation of Evelyne Costes.
So good afternoon, everyone. So I'm going to thank Ian and Frédéric for having invited me, and this is not for joking, but real. And if we think about the classification that Alexis propose us, I am clearly on the academic side, and I will not talk you about yield. So I will talk about a use case, which is quite exotic here, and I will talk to you about fruit trees and apple tree, which is my favorite species. I come from a GAP unit, which is in Montpellier. And we are, the first motivation for this study was the genetic variability of tree shape, of tree architecture. I propose here two different illustrations, one for peach, one for apple. And in both cases, you see that we have a huge variability in both topology. It means number of axes, how these axes are organized along the trunk, and so on. And also the geometry of the tree. Is it open? Is it narrow and erected, and so on? Why are we interested on the tree development and architecture is because it is a key feature for the fruit production, even if I will not speak about yield, and also in the way the tree will interact with the environment, especially in the climate change conditions. Because the canopy structure will define the light interception, the way the plant will interact with the atmosphere, with capture of CO2, and will lose water. We did in the past some in silico modeling to try to figure out how we could combine tree architecture with functioning traits, and how we could achieve nice ideotype for breeding. But this is quite theoretical, and actually how the traits combine in reality in collection of diversity was not so well studied. And the genetic control of the two type of traits was never investigated because really because of major bottleneck, which is the phenotyping. It was not possible to capture those traits in large populations. So we really addressed this question, how we could phenotype for tree architecture and functional traits at the same time on trees. So our strategy was to combine different approach. So for the tree architecture, we decided to go for terrestrial LiDAR to try to capture the geometry and the topology. And we combine that with airborne imagery for calculating vegetation and disease from multispectral imagery, and also with thermal camera to capture stress and disease through the temperature of the canopy. We also collected some more classical variables like production, tree cross-trunk sectional area. Of course, when we started this, this approach, we had to validate because with high throughput measurements, we have proxies of the variables, so we need to validate with in-planta measurements before going for genetic analysis. So this is the way we followed, and what I will show you today is the result we got during a postdoc study made by Haute-Coupe-Ledry, and we did two main papers in 2019 and 2022. The experimental design was near Montpellier in a Diascope experimental unit. We are having a collection of 241 genotypes multiplied 4 times and displayed by couples twice, two times, 2 replicates. The plot is micro-irrigated. And we are having some meteorological and soil water status follow-up. What we did in this experiment is to apply a water stress withdrawal, so water stress application. And we did that on different rows. So you have the rows in yellow, which are water stress, and the blue, which are well-watered. And we put tensiometers, capacitive probes all along the rows, to follow the soil water status. Here you see the dots along the rows. Okay, so the field acquisition for terrestrial LiDAR, we did 2 campaigns, one in summer, one in winter. And we took 1 scan every 5 trees on each side of the row. We got this kind of images, then we had some data post-processing for filtering, removing the soil, the wires, and also to segment the trees because each tree was a different genotype. And you can see that, as I told you at the beginning, the shape are quite different. So we had to analyze tree by tree. Then we used a tool for 3D reconstruction of the shape. This was done on the winter trees. And from that, we tried to extract some variables. So for the topological variable, we were extracting the number of axes, and we tried to characterize those axes depending on their lengths. Here you see the results for total number of axes, but also when we classify by long, medium, or short, you see that for the short shoot, we do not estimate very well the number of short shoot. We compare what we get with the LiDAR, with a manual digitizing system, on a subset of trees, of course, because this is quite time-consuming. And you see that if we consider the total, it's pretty good. The long and medium axes are quite good. But what makes the regression to be lower is because of the short shoot are not well estimated. Then we estimated, I think here I should go, I have some, yeah, okay. We also estimated some geometrical variable. So we took the dimension, the height, and the diameter of the tree. Then we calculate an envelope, a global envelope. We call it the convex L. And then we curved this volume by a circle, and we made vary the diameter of this circle to really go toward the estimation of the plant leaf area. So here again, we used a subset of measurement in which we calculate the total leaf area of the trees. And we saw that we could find, for diameter of 10 centimeter, we got the best correlation between the observation and the estimation. Also, we calculated the leaf area profiles for different trees. You see we can have different maximum leaf area depending on the shape of the tree. And from that, we also calculated the total, the silhouette to total leaf area ratio, the star value, which is a proxy of the light interception. So we take the projection of the tree in different direction, and we look at the projected leaf area on the soil, and this makes an estimation of the light interception in all the direction of the light. Then from the imagery, we used the multispectral camera from IFEN and also a thermal camera. So we had different wavelengths from which we could calculate different vegetative indexes, which are quite classical, I think, and also different indices to estimate the level of water stress we have, the difference between the leaf temperature and the air temperature, and also some indexes of the level of the water deficit perceived by the trees. Just a precision on how we calculate the temperature of the canopy. So this is what we get from the drone, from the camera. So what we did is to take each tree, a circle at the middle of the tree to extract the pixel and to compute the mean pixel value per individual tree for the well-watered trees and the water deficit trees. The idea behind, of course, is that if the stomata are closing, the leaves will be warmer, and this will reflect the water stress. So here again, we compared this value of temperature of the surface of the leaves to the temperature of the air, compared to the measurement of the stomata conductance by porometer. And again, we said, okay, we had a good proxy of the leaf functioning. Okay, so now some result from those variables we extracted. The first result is that we got a large genetic variability for the architecture and light interception traits and for all the vegetation indices. On those traits, we didn't have any effect of the water deficit we applied, probably because I didn't tell you that before, but we applied that water deficit during 1 month in July, and the apple trees had already stopped growing. So they had their flush of leaves. In April, they grow, and then during June, they usually stop. So the water deficit was applied after the leaf developed. So we didn't have an effect on all those variables. However, all those traits were highly heritable. We had very good level of broad sense heritability for all of them, and we could classify them depending on those variables in different groups. Here you have some example of tall trees, not so dense, and shorter trees that are more dense here. Okay, I will go quite rapidly on that one. If we do correlation between traits, we see that on that population, light interception is not necessarily correlated to the vegetation and disease and to the tree architectural traits, because we could have small trees very dense and small trees less dense, so we can decorrelate the two types of traits. If now we look at the variable of leaf temperature surface compared to the air, here we have this variable for the well-watered trees, and you see that this variable is not constant on the different date in which we had the flights. So this is the first date, and then during the month of July, we had a progressive increase of this variable. Probably here we are in the well-watered trees, so the soil, the soil potential, water potential is quite constant, but still probably due to the evolution of the temperature and the VPD, we still have a variable temperature of the leaves. So we had a calculation of one data for all the dates, but we had to account for the data effect on the genetic analysis. Then what happened to the trees that were water stressed? So you see that here, if you compare in red the water stressed trees to the well-water one, across the date you have a switch between the well-water and the water stress, and this difference increased with the water deficit. So we were happy. We said, okay, it's working well. But the irritability was less, probably because of the shrinkage of the variability within the population. So I will not go into the detail of the genomic data. We had a SNP array data set. And we did a GWAS analysis, quite classical one. What I would like to stress on those results is that we got association between the phenotypic trait and the genotypic data sets. Here you're having the log value of the log of the p-value, so the significance of the association. What is interesting here that we got different association, but the portion of the genome that is associated for each kind of trait is different. So this means that we could have allelic combination. So if here we have in green the architectural traits, in brown the temperature of the leaves, and in yellow the light interception. And you see that the different genomic regions are associated with the different rates. This means that for breeding we could combine different allelic variation within ideotype, and those combinations are quite independent at that step in the collection. So I have finished to present you the results. So what can we conclude from that studies? So first, we were able to simultaneously assess the canopy vegetative development, the canopy functioning, and from that to classify the trees depending on their global shape, their architecture. And we were able to assess that the proxy we can capture with high throughput phenotyping are relevant if we do more precise measurement on the trees. We can say, okay, the high throughput is working pretty well. We can rely on that. The third point is that doing that, we can capture genetic variability, which is a good point, and that we can have multiple allelic combination for all those traits. So we can combine and we can look for different phenotype in this collection. What is still pending as a question is how we can define or evaluate the water use efficiency when we are working on a medium or long-term crop as a fruit tree. What does it mean to save the water on one cycle? Which consequence this will have on the next cycle? So we still have to define exactly what we want to select and what we want to evaluate. But we have the material to do that. So thank you for your attention. I would like just to show you the person we were involved in this study. So the member of the team we were involved, of Coupel-Lebris, Benoît Pallas, Jean-Luc Régnard, Magali, who was involved in the images acquisition. We had also the help of Laurent Albrecht for UMR Tétis and Frédéric Boudon for the liDAR acquisition, and Vincent Ségur, Hélène Muranti, and Charles-Éric Durel for the genetic analysis. So thank you for your attention.
Thank you very much, Evelyne. Okay, maybe just one short question if we have. Okay. Oh, Fred.
Thanks, Evelyne, for this nice illustration of what you can do on our charts. My question was related to the estimates of the Lipher index from LiDAR. Why didn't you try to use the transmittance that you can get quite easily from the LiDAR rather than from the convexel or the alpha envelopes?
Yeah, we could try. I think we had this information of the convex L and the density of point within, and it correlated with the leaf area. Probably we could do differently. You're right. Yeah, sure. We can try. Thanks.
Okay, thank you. Now we should move on to Professor Wei Guo from Japan, long way.
Good afternoon, everyone. First, I would like to thank the organizer committees to make this wonderful program that really attracted me to be able to, it's pushed me to be able to join this conference physically. It's very difficult for us to travel abroad. I think without this wonderful program, I might be still like this cyber me, hidden behind the monitor to give my presentation. So my title would be more focused on the edge computing for the plant phenotyping. It's just because we actually a brand new laboratory which is called Field Phenomics Laboratory in Japan. I think this should be the only one official laboratory which is focusing on the phenotyping in Japan at this moment. I would like to spend a little bit of time to introduce ourselves to all of you a little bit. And please forgive me if the quality of the presentation is not good enough. That's not because I spent too much effort to travel to here, to be prepared to here. It's just because this part is more like the academia person who is playing with all those kind of hardwares. And I would like to share the failures that we had until now. So a small introduction of us. So our laboratory, we have actually two bases inside Japan. One is inside the middle of the Tokyo over here. So everything is super expensive. And we have a big farm inside the Tokyo city. And you can travel from center to the field for just 20 minutes. So here's me as a brand new PI of this laboratory. And we have several colleagues who is coming from the totally different background of this one. And this is actually a digital farm, digital twin that we made for this field. So this is a brand new building of our campus. The money is coming from that they sold the land to build this road to the government. So another bit, maybe you can close the voice. Sorry. Another bit is actually very important for this talk is Hokkaido. So basically, you image that the farmland in Japan is tiny, small farmland and tiny, small experiment field inside Japan. However, we had this good experiment field in Hokkaido. So if you check the average area of the farmland of this area, it's almost as same as the European scales. And they are more focusing on the crops that not paddy rice. So you might know that in Japan, a lot of people are working on the paddy rice a lot. And the most important thing is this village, they actually investigate a lot of money to our laboratory, and they have a huge amount of the tractor robots. And you see this is 5G tower inside the field. So this small, tiny, small village, they have 5G towers inside the village. So they are trying to make a super village inside Japan to be competed with the traditional Japanese farm style. So I think this would be a big opportunity for us, as well as the collaborations in between us and here, because the scale is almost as same as France now. But we just started this year, so it's not too much effort we had at this moment. So I hope I can present to you later. So the research topics is more about those one. Mainly developing the algorithms that are doing phenotyping based on the images, but we also do the field sensing. We also do the real-world applications, and we have startup projects. We have receiving the money from consumer companies at this moment. So just a quick introduction of the field sensing techniques that we had for more than 20 years, I guess, from Professor Hirafuji, connecting the image and environmental data across tested all over the world. And the robots, I will talk about it later. A lot of toys, I have to say. Nothing can be used as the product as haven't delivered at this moment, but it's just like academic side of things. But the good thing is everything is open sourced. And then drones, we also play a lot with the drones, and I also teach students how to operate the drones in the field. So you see, this is a style for more than 2 years that we have now in Japan. Every time, even you teach in the open field, you have to wear everything, uniform and masks, everything perfectly. And we started to running this drone project since 2011, so we are actually holding the patent in Japan as well for drone-based phenotyping as well. The most important part is here. Since we do not have fancy techniques to connecting the data, so we build those IoTs, those robotics, those drones to connecting the data from different scales of the plants, and then develop the algorithm to process them. Then come to the main topic of today, edge computing. Why we are trying to use edge computing? I just show you some of the examples that the breeders ask us to provide to them. So we actually, in Japan, we are kind of service providers from the academic side, but without receiving the salary. So this is the sugar beet. They are looking for something that they can present the hybrid vigor of the different varieties. And this is shore paddy rice. They are looking for some early flowering paddy rice varieties that can defend the global warming things. And another thing is paddy rice like this. So they are trying to know the growth stage of everything. So here it actually comes to the most important part, why we need edge computing. So we have the pictures, right? We put an IoT camera into the field. We have like at least 3 to 10 megabits of one picture. And if you take like 8 pictures a day, you have a lot. And but the breeders, what do they want? They actually want this one. So a graph that can present the growth, the dynamics of the growth of their crops. And they want this kind of data every day. So if we deliver this one to them, it's a super simple way. But if we wanted to deliver this one, I have to tell you, even though we have the 5G techniques now inside our field, it's still a problem to transfer a huge amount. So the amount of the image is huge, right? So you are not transfer a one big file. You are transfer a huge amount of the small but still big files to your server. So that's a lot of work. That's a lot of resources that we need to use, especially recently. Every people need the internet. You use this one, you send a lot of pictures a day, you waste the bandwidth for them. So we wanted to deliver this one. And then we started to think about a good edge device for phenotyping could be. So two parts. The hardware part, it should be easy to use. It should record everything over here. So actually, I think I would recommend lateral. It's already a little bit old. But anyway, so this is the things that we need to have from both hardware and software side. So we had this thing 2 years before. So it's called EasyRFP. But it's actually not so easy. I will tell you why it's not so easy. But basically, it has everything that we would like to have inside this box. And my thought would be, if I bring this one to the trials, for each plot, I just bring them to each plot. I get the phenotypic traits that I would like to have. Okay. So because it's from 2020, as you know, everything stopped because of the COVID. So we cannot go to the field. So the first trial became to like, I just present the weight. So this is a picture from Global Weight. I present the weight pictures on the screen and make the system to capture the screen to check if the whole system works well or not. Looks great. I said, yeah, it's working very good. So I started to deliver these two different modes for this edge computing systems. One is a real-time mode, which means you just take the counting the weight head as an example. You bring this one to the field, you just take a picture, you get the number of the head, and you go to the next plot. Another one is the schedule mode. So this is more for watching the dynamic traits for every day. So for example, the breeders in Japan, they would like to know the flowering time of the paddy rice. So I just make this one for them. Like you put this into your field, from morning to the noon, you just get an email with a CSV file that can tell you when will be the flowering time of your trials. So it looks wonderful, and we had this one very good. And then I bring it to the field, and then I realized this is the application, looks great, and you have all the systems from the GitHub. If you would like to try, just go and download everything and try it. It uses Jetson and the normal cameras. But the thing is, it's not easy. Why it's not easy? First, it's too heavy to carry. I carry this one from my office to the field. I almost spend most of my powers. And it also have some problems with the power supply. So it's not difficult to deploy. I think it should be good for the fixed point observation, but not the thing that I'm expecting for. So it's a failure. But it's worth to try for the first edge computing things. And also it's not moving smoothly. So next we started to think, okay, how to make something that can move a little bit easier for us. So it comes with this one. So this is actually another open hardware and software project that we made for the Japanese wheat breeders. So the most important concern of this project is here. So I think you show a lot of great plots here for your experiment field, but in Japan, 25 centimeters plot. This is what you can have. You see, every plot like this. So, and you have a lot of troubles if you wanted to run your robot smoothly. So this is because of the location limitations here in Japan. So we run small trials and tiny small things like this. So, and it's inside the city. So it's Kyoto University. It's inside the city. If you think about the RTK GPS navigation systems, I have to tell you that's not going to work because you have all the high buildings around you. So it's not the thing that you could have. So okay, we started to think, okay, maybe edge computing, not just for the phenotyping. It also could be something that we could have for the navigation systems as well. So we had the first trial. So basically, I built this one first. I think it's good enough. But however, the result is like this. The balance is very difficult. You know, the balance of the things. So it's not working properly. So we have to change that to this DOA style things, and especially inside the field, you have to make it work stably. So we had this conception of build mostly focusing on how to navigate this system to make it running super precisely inside that tiny small breeding field. So this is the most important part. And also, you cannot make everything fully automatically because for example, for this field, we have like 3 separated small fields, and in between these 3 fields, you have a block. So you need to ask the operators to do this operation sometimes because your robot cannot work perfectly with all these complicated situations in our field. So here it is the thing. You see this one? So we even have to build a bridge to make this robot go from this side to another side of the field. You see this one? This is a little bit a long video, but I will explain you all the details during the video. So you see it's running like this, and we put the markers every 50 centimeters to navigate the robot. So once you have this one, you see this this robot, it's actually working very sensitively, right? So it's every time it's moved to make sure the center of the plot, the plot will be at the center of your robot. So that's very important for our later phenotyping tasks. But we do run this thing like this, so it works good. But you still have to operate them when you want to cross the block. So this is actually the thing that we do for the navigation part. And since we had this one, we are being able to collect a stable data set from these systems. So 1,000 plus plots in these 3 different blocks of the field, it will only consume us for 1 hour to collect all the data. So that makes us to have a huge high frequency of the high resolution data for the whole field. That's why we can do this plot segmentation. So this is totally different plots like what you can image, 25 centimeters plot, and then you can calculate the dynamic of the growth. You can for sure calculate the hiding date, and you can also calculate the dynamics of the flowerings of each different varieties. That's great. Just because we have this kind of things. So the summary of this one, so you see, I just name it rover, not an easy rover. Why? Because I know I cannot make an easy thing to do it. But so the feature of this one is like it have 2 modes to operate the robot, and it have also 2 edge computing part to do both navigation and camera control and phenotyping. However, if we wanted to do this real-time phenotyping, it's still very difficult because the plots are so tiny small. So it's very difficult for us to segment those plots like in real time. So we do the 3D reconstructions and then we do the reverse calculations to back to the plots. Also, as the last, I would like to share some of the other related works that we've been working related with this edge computing things. For example, we do have this kind of device to do the real-time 3D reconstruction. I don't know why this video is not working, but it's a handy 3D thing. You just move your handies and you have the 3D structure of your trace. And also we do the efficient training data acquisitions because the most important message from my side is like I pray for lots of locally good models instead of one global good models. So you know deep learning, it works good, but if you change your domain a little bit, you will have a very affected result. So what we are trying to run at this moment is to connect the training data for each different tasks. But we do not want to do this training data connection manually. So we have developed a lot of different strategies, include this one. You have a fake apple or fake tomato on the top of the real orange trace. And then you will have automatic annotation for it. And finally, we think the edge computing could be a little bit more advanced. So we started to run this trial like this. We combine the energy harvest, data storage, sensor network, and phenotyping together inside the field to deliver this kind of things for the field-based edge computing things. And the summary of this one is like, I have to emphasize that edge computing actually depends on the different purpose of the tasks that you would like to have. For example, for this one, because your robot goes through the whole row of your fruit trees, and you have a lot of overlaps of your pictures, that then you would be definitely need this kind of things to track and count the number of the fruits on real time to avoid the double counting. But for the drones, it's good to have the edge computing, real-time phenotyping, but if you think about the operation of the drones, you have to fly it and you have to bring it back, change the batteries, connecting the data. So you have to touch it all the time. So which means you can have a chance to process the data after the drone coming back. So maybe for this part, we do not want edge computing on the top of the drones. It might be good for some part of the station later. And then the last, I was so surprised, and I added this one 2 days before. So I saw this highly technical drones, swarm drones that you can run from the field. Then that would be another step of the edge computing of the drones. You cannot see this video, but Google this one. You will see an amazing video about these swarm drones. Okay. Finally, I would like to thank all of my colleagues, and I'm happy to receive questions from all of you. And you can access to my email address or check the papers that we had for this brand new things. Thank you very much.
Thank you. Okay, thank you for this fascinating presentation. We are a bit late, but if maybe very quick question.
Sorry for spending too much time.
Thank you for the very nice presentation again. Have you tried edge cloud computing with the computing power at the foot of the antenna?
No, we don't. Yeah.
Maybe with the 5G infrastructure, it could be.
Yeah, we would like to dig it out. Yeah. Thank you very much for your suggestion. Okay.
Okay, thanks a lot. And the next presentation, it's actually not in presence, so it's remotely. So maybe we can start.
Good afternoon. Thanks to the organizers for the invitation to speak at today's workshop. First, I'd send my regrets for not being able to attend in person. I know that I've missed out on some great French hospitality in Avignon, but I do hope to be able to see many of you in person at the IPPS conference this fall in Wagenhagen. In the talk today, I would like to present some broad ideas around the use of deep learning within plant breeding research. And we'll start with an overview of the capabilities of deep learning, how they map to specific opportunities in plant breeding, and then some of the grand challenges in this area. So why are we interested in deep learning generally? It really is in response to the rapid increase in the availability and the measurement of agricultural data. This increase in data set size and breadth has really three main areas. The availability of genomics data has increased rapidly, and the costs for performing sequencing have reduced dramatically. In phenomics, measuring plants grown in the field or in the lab has increased rapidly over the last 10 years, particularly in Europe and Australia. And then over the past 5 years, we've seen a huge increase in North America, kind of catching up on the rush to generate phenomics data. And then finally, the availability of agronomic data, large-scale agronomic data relating to weather, rainfall, soil characteristics across the food-producing regions of the world has also increased dramatically in the past 10 to 20 years. And although we have this significant increase in data, bringing these data sets together is one of the main challenges. And this is where we feel that deep learning can play an important role. This need to transform data into actionable decisions across the agricultural value chain. So this is including plant breeding, growing plants, as well as food processing and downstream activities in the food production pipeline. But that's sort of the basic idea of deep learning. I think that there's a few main aspects of deep learning that make it quite a powerful approach and particularly well suited for opportunities in plant breeding. The first is that we can learn features across multiple scales. So these could be spatial scales where we may have very close-up pictures of individual plots in, say, a nursery trial, larger microplots in a yield trial, or even larger satellite images across producer fields. And the same deep learning approaches can learn features across these multiple scales. We can also think of the spectral scale if you have multi or hyperspectral images where we can learn features across the spectrum. And if you have sequences of images over the plant's growth life cycle, we can also learn features across time. So these time-lapse images are of a canola field from the research fields at Agriculture Canada. And in particular for plant-based data and growth cycle data, we think that these temporal features can be very important. These time-lapse were captured by our camera on a stick that we developed for capturing long-term image sets over the growing season. The other important aspect of deep learning is that we can learn features across data types. So the same or similar deep learning architectures can extract features and learn across images, also across text-based data. So these could be labels that have been assigned to images or particular microplots, canola, flowering, pods, sort of the breeder notes that they might take while observing the field. But these could be also text-like data, so genome sequences or other structured data that has some structure that we can take advantage of. As well, categorical data, such as breeder ratings on a scale of 1 to 5 or 1 to 10, growth stages that are in categories, or particular treatments of an experiment. So if you have an experimental setup with particular categories of inputs or stresses applied, these categorical information can be also incorporated into these same deep learning architectures. And then as well, time series data. So if you have time series data across the growing season or across the day, even these time series data, there's also mechanisms to bring those in. So now that we've discussed some of the basics of deep learning and what the potential of deep learning is, let's see how these map to some of the opportunities in breeding. So I think the first and foremost opportunity is the potential to increase the scale of plant breeding analysis. And since the objectives of plant breeding are to generally increase genetic gain, having a larger number of examples to observe over is one strong and clear strategy for improving genetic gain. These field pictures are of the wheat program by Curtis Posniak, and you can see him here walking through the field. So this increase in scale could be, depending on the breeder, could take different forms. It could be just a larger plant population, more lines to select from at each generation. It also could mean a larger number of field sites, so trying to capture the environmental variation imposed on plant growth or plant production from different environments. So another opportunity that deep learning provides is the chance to increase the efficiency of a breeding program. So in general, with deep learning and efficiency, we often talk about automation or think about automation. So trying to remove or automate tasks that are tedious or time-consuming for people to do with an automatic approach. In our program, we often think not of automation in this sense. We do see the tremendous value of experts, plant science experts, plant breeders. We recognize their expertise and we value it. And so often we think of efficiency more as trying to take those the human resources we have, the expert resources, and deploy them in the right place and the right time. We often think of this as a triage approach. If you have thousands and thousands of microplots or lines to investigate or interrogate, we think that it might be difficult for a deep learning model to pick the best line, but we do think it's reasonable for a deep learning model to identify the poorest performing 80% of the lines, for example. The last opportunity that I'd like to mention is the opportunities in marketing and ESG initiatives. ESG here stands for environmental, social, and governance initiatives. So many organizations, both in industry and in public sector, are working very hard to try to achieve or to contribute to large-scale sustainability goals. These could be the Sustainable Development Goals from the United Nations. In Canada, we have a new policy framework at the federal level called the Healthy Environment and Healthy Economy policy. And then more particular, in agri-food, there is a movement towards benchmarks and indices to measure how sustainable the agri-food sector is. And all of these, responding to all of these challenges in this area really has to be grounded in data. Really feel strong it has to be data-driven. But getting that data into a usable form that's understandable by stakeholders or customers is a big challenge. And this is, again, where we think deep learning can have an important role here to take these large data sets or what data is being collected and generate from it actionable information, actionable here that's sort of visual, intuitive, and responds to the particular requirements of these initiatives. So if those are the main opportunities, there are a number of important challenges to actually respond to those opportunities. So the first challenge is on efficiency. So efficiency is an opportunity, but also a big challenge. So although deep learning analysis has the potential to reduce the amount of manual inspection of plants in the field, having technicians and breeders walk through fields throughout the growing season. It also requires typically annotated images or data sets to learn or to train with. So one important challenge to keep in mind is that there is potentially not much benefit to replace tedious field work with tedious image annotation. And this is particularly the case for large data sets. These are examples from the global wheat head data set that I'll talk about in a couple slides. But you can see very quickly with these large data sets, they become really, really costly to annotate. But another aspect that can be potentially challenging for deep learning models is by triaging or removing lines or parts of the data set from the model to gain efficiency. If this reduces the variation in the data sets, that can also have a negative impact on model training. So I think there's a couple important characteristics or considerations of efficiency. One of the areas we've been pursuing in my research group to address these is active learning-based approaches. So active learning often is phrased in terms of annotations. So which are the most informative images to annotate? So imagine these examples from the global wheat head data set. We have thousands of unlabeled images in the most recent version of the data set. And we would want to select the best ones across these data sets to annotate. And it might be not necessarily that we want to annotate 100 images from each domain, each country. It may be that certain countries have less variation, and a fewer number of images is required to achieve the same level of accuracy. So active learning provides a number of tools to try to help make this decision of which images are important to annotate. The same idea of active learning can be also applied to this triage problem as well. And we would state this as which are the most informative lines to bring forward or to replicate across environments. So we might need to do a little bit more, so maybe bring lines forward or replicate things in ways that, that provide sort of enough variation in the data set to make the deep learning model more robust. And this, I think, also can be phrased or formulated under these same active learning type approaches. Another important challenge is, for deep learning models is distribution shift. And this we can discuss as wanting, often we want models that we've trained to work outside of the training set. In fact, this is really the sort of one of the main goals of deep learning, is that to train a model that works well on unseen data, this sort of test set data. But in terms of plant breeding, this can be actually much broader, because we may really want to use models far outside of their training set. We might want to use last year's model in this year's growing season. We may want to use models between very different environments. Use a model trained with images of North American crops in South America for a winter cycle season, and across species. So, using a maize model on sorghum images, for example. There's a few, two main ways that we can try to address this distribution shift challenge. One is a technical approach called domain adaptation. It's adapting a model for use in a new domain. And another approach is to actually just generate more diverse data sets to begin with to make more robust learned models. So we've done some work in domain adaptation. One paper that we published in 2020 was to adapt an indoor model to outdoor images. So we used as the source domain the ACID dataset from the University of Nottingham of wheat spikelets annotated from these really nice, beautiful indoor pictures of wheat plants on a black background. So these indoor or controlled environment images are often easier to annotate, easier to access, and provide a good training set. But due to the limited variation or the differences from the indoor environment to the field condition, using them directly can often doesn't result in good performance. So we attempted to use an unsupervised domain adaptation approach to take this indoor trained model and then tested it with two different outdoor data sets. And just quickly, the results of this model were promising in that, so these are the outdoor images from the one test data set, the ground truth spikelet annotations. If you just use the indoor model directly in kind of a straight transfer learning approach, it really doesn't work really well at all. It kind of identifies where the wheat heads are, but really has no discrimination on individual spikelets. Whereas the adapted model that's gone through this domain adaptation does a much better job of identifying individual spikelets in the rightmost figure. And again, this adapted model requires images from the target domain, these outdoor images, but did not use any annotations on the outdoor images. So it can potentially reduce the annotation effort and cost substantially. And of course, the other approach is just to generate more diverse and larger data sets to begin with. And this is a particular challenge in the area of plant images. You know, for a number of reasons, you know, they're challenging. These data sets are challenging to collect. Often, an individual data set is quite self-similar. You know, there'll be some variation within a particular field site based on the plant population and the genetics of the plant population. But certainly, there's much more variation between crop species or across different environments. And so I expect that the global wheat head data set has been mentioned already in this workshop, but I just wanted to highlight again what an awesome and excellent collaboration this was. I think in the latest version, we had 17 international institutions participate and provide data. And certainly the Arvalis and INRA team provided, you know, strong leadership and I think provided the largest amount of data to this initiative. So certainly we strongly commend the French group for their contributions here. But briefly, the other aspect of just collecting the data set was that we organized two AI competitions, one on Kaggle and one on AI Crowd. And so in addition to this excellent data set, I think we've cultivated a community of AI researchers that are more aware of plant problems now. You know, in the Kaggle competition, we had over 2,000 teams participate. And you know, I think one of the strong results of that is that many of those machine learning researchers would have never seen pictures of wheat heads before, and now they have an understanding and an appreciation. And I think we've been able to recruit or attract more people to these important plant science and plant breeding problems through this effort. So again, big congratulations to all members of the global wheat head team. The final challenge I wanted to mention was that of recruiting talented individuals to work in this area. Of course, data scientists are in high demand across all industries, but we do feel there's a need for dedicated training for data science in agriculture. At the University of Saskatchewan, we have developed a computational agriculture training program, and I know there's a number of similar programs across North America and in Europe. And we really think this is critical for bringing together plant science students together with computer science students to do that cross-discipline training, to understand how better to work together to get basic skills for computer scientists in biology, as well as basic foundations on data science and computer programming for plant scientists. This is a picture of our computer science students on one of the field days in the training program, where they were able to get out to the field, get hands-on with collecting plant data and getting a better appreciation of the effort needed to collect images and collect ground truth information that they're using to train deep learning models. I also wanted to mention that there are a number of programs in Canada for international exchange or student internships, particularly between Canada and France, but also with other European countries. So I think there's a lot of opportunity for cultivating these talented individuals and enriching their experiences through these types of exchanges. So thanks again for the opportunity to speak. In summary, I hopefully have provided an overview of where I think the most important kind of features of deep learning map to opportunities in agriculture, opportunities to increase scale, efficiency, speed, and to support new types of sustainability initiatives. And then I hope as well to have emphasized some of the challenges that we have. So domain shift, data diversity, and people training. So thanks again, and I'm happy to answer questions now. Thank you.
Thank you very much. Any questions? So. Okay.
So we've tried counting wheat heads also from moving vehicles like drones, and tested some AI. Have you tried with a global wheat head data set to make it artificially blow in the wind or fuzzy or something to see how these models, these adapted models, might hold up?
Excellent question. I do think that there's additional challenges in these situations where you have moving vehicles, additional blur. And I agree that these artificial augmentations are good ways to explore the effect of these possible sort of image challenges like blurring on the performance of models. But we've done some work with these synthetic data, and I think they work to a certain extent. But I do think that having reliable or real-world test sets of these conditions is very important as well. It's hard to simulate sometimes what the actual aberrations are.
Okay, thanks. I think was a question.
Not a question, just to conclude.
Okay. Any other question? Apparently not. So thanks a lot for being linked with such a long distance. But okay, thank you very much. So this will bring to an end of this session, and also an end to the workshop. So I give the word to Fred for some conclusions.
Thanks very much, Raffaele. So yes, at the end of the two days session today, so we were about 100 people here, and in the web there were, well, it was changing, but between 250 to let's say 100. It depends on the time. So I think from the attendance, it's not too bad. I think there was quite some good balance between web presentations and in-person presentation, so that was not too boring, because sometimes the web presentation is not the same, so it's not too bad. So we need to thank very much the people who participated to the organization of the workshop. So thanks very much to the Hyphen people, and especially Nicolas, Etienne, and Gladys. Also to Arvalis people. To Arvalis people who welcome us, so Delphine and Céline. And also to Jérôme and Nicolas, who were phenotyping us with the camera. Okay. So very quick words about what at least I remember from this workshop. So we were seeing quite a lot of traits and species, which is good, and not only let's say great crops, but also some strange trees and vineyards and things like that. So I think that's quite good, and with new questions. There were not too much emphasis on the observation systems, even though thanks to Wei, we saw very fancy systems and some kind of risky one also. So there were more aspects on the methods used to estimate the traits. There was quite a lot of use of process models in the retrieval process, but also in the later interpretation of the traits. Quite different scales between, let's say, the canopy with satellites, but not only. The plant and organs, and even the disease, so very small scale in the organs. Different methods for the same traits, but not too much ensemble methods, so maybe that's something we should look for. There were some suggestions to combine the use of several sensors, but not too many examples, just a few. So maybe that's also things that we should look for in the future. There were some applications shown for the gene discovery that was quite interesting, successful for some of them. Not too much on crop management. The use of phenotyping for crop management was not the main issue of most of the presentations. So finally, I think I saw, that's my feeling, that everybody seems happy, but I don't know if it's because it's the first conference after the COVID. So thanks for the COVID. Or maybe you find some interest in the conference, in the workshop. So anyway, we hope that you enjoyed it a lot. So maybe before closing the session, if there are some comments on the format or the content of the workshop, so we are very pleased to discuss it for a few minutes. So it's open to the floor.
Maybe can I ask, will the presentations or the recording be made available? Or
I think so, yes. It's recorded.
So yeah, well, to answer the question, Raffaele, as I asked yesterday, if all the presenters are okay, all the slides will be shared with the attendees that were in person, and all the sessions and online movies that we recorded during the 2 days will be also available online. And we all have your emails, so watch out, we'll send you something. And also for tonight, I can mention that you received an email from contact@-plant.com, just telling you a few bars and restaurants to go to if you want to enjoy the evening. And make sure to have a good evening in Avignon, and see you tomorrow for those who are staying. And yeah, until next time.
Is there anyone who wants to comment, or
maybe later?
Sorry about that comment, and you cannot be re-released now. What is the difference, I'm just curious, between a workshop and a conference? At the workshop, are we not supposed to work something? But there was no shopping included either.
My feeling is workshop is a smaller event where there are more discussions than conference, where it's maybe more academic, more formal. So that's what we try. That's why we were saying workshop than conference. And conference, it's more bigger events and more official, I would say.
Maybe for the story, actually at the beginning it was the CAPTE days, and then there was a big debate on whether we should call them CAPTE days or CAPTE workshop. But in fact, workshop is quite nice because it was a time where we shared all our works that we did during these past years, 2.5 since the last conference. And it was, I think, in a more maybe less formal way than in a conference. So we hope you felt like that at least.
Then will you redo this kind of workshop next year, maybe?
From my side, no.
So okay, well, I think it's a good format at least. So and we were very pleased to welcome you. So we can think of something else. So probably not next year, but in the coming years, if we can do the same kind of event, it would be great, I guess.
Yeah, no, maybe to say, yeah, so it's the end of CAPTE as it's has been done, so for the last 10 years. So there will be new format of what's happening in Avignon, and all that is being prepared. And so I think we'll try to make events like that every 2 to 3 years. I do believe it makes it makes sense. So today we're still trying to figure out the format, but if you have any ideas, we're always happy to get your feedbacks.
Okay.
Maybe also one difference with usual conferences is that here we invited most of the speakers. So we selected a subject and the speaker, so that's also another way to do meetings or conferences between differences between conference and those kind of workshops.
Okay, so maybe we can close these 2 days in the room session, and so thank you again for your presence here. Hope to see you tomorrow for the field day, the great field day, and good evening.